So let's get started. Thank you all three for joining this SOFA session. So it's an online course. Sometimes we organize it more like just like for the SOFA Week 2023, like also on-site courses. So the course of today will be really like an introduction course to SOFA, and it will be split into like four main parts. The first part for this morning will be an introduction about SOFA. What is SOFA? What is like a physics engine? How does that work? How does the community work and how it is organized? As a first step, it's like not the first thing useful if you want to get started with SOFA, but if you want to get started to work with SOFA and its community, all this information will be actually pretty useful for you guys. As a second step, and we'll start this morning and continue this afternoon, it's going to be using SOFA. We'll start building a simulation step by step. And the purpose of that is to understand first the principles of how to build a simulation, and also sometimes some relationship which exists between components and what makes actually the whole SOFA simulation cycle work, like at each time step, what happens, what is computed, and so on and so forth. We'll continue in the afternoon with this user tutorial, but we'll focus not anymore on XML scripting, but on Python scripting. For that purpose, we'll check together if you have like a SOFA version working. So the latest one is currently the 23.06 release of SOFA, and using also the Python bindings coming with it. And finally, it will be pretty short because we actually decided to shorten a bit this part to make the relationship between the whole user tutorial, how to use SOFA, and starting to uncover a bit like basic, I would say, mathematical and mechanical theory which is behind, and most importantly, a bit the code, just to have a very, very short overview of the code so that you feel something that I did not feel for some time when I started SOFA, basically that there were no magic under the hood, right? Like when you click a button, there is a set of calls in the code, and to just understand what exactly happens when you click there and when you click there and when the simulation time step is computed, okay? So it's an introduction course to SOFA, bringing backgrounds and basics on how to use SOFA. And just so that you know, I think it could be of interest for you, Guillaume, and Ronak as well. I think we'll plan some additional sessions later on. Actually, for you, Carolina, we mentioned that also, but maybe more robotic oriented, but to have some additional sessions where we would focus on specific I would say specific part of the simulation, or a specific, more scientific part of what happens. Could be on constraint resolution, on mechanical models, solvers, integration schemes, that kind of things, which are a bit more theoretical, where a bit more background is needed, but at least this background course is definitely needed to get started for the other courses. Okay. So let's keep that interactive. I actually firstly would like to thank you for all keeping still your camera on, because it will make things also a bit more interactive. Anytime you have a question, you unmute yourself. You can also raise the hand. I have another screen on the right so that I can check that myself. But if I don't see that, just unmute yourself and ask anytime the question you have. Okay. So just a word about myself, just so that you actually know what I do know and what I maybe won't know, because I'm far from knowing everything about SOFA. So I'm a mechanical engineer. That was actually my background more than 10 years ago. I started with SOFA by doing actually a PhD with SOFA. My thesis was about nothing about mechanics, but more electrophysiology. So say electrics, but it's more electrophysiology, the electrical activity of the heart that you see on the top right. So basically, I actually not really worked with SOFA for almost 5-6 years until I started another job, the position that I currently have, which is taking care of the project somehow. And there I started going back to mechanics, mechanical engineering, and really understanding the engine, which is SOFA. So there is still part of SOFA, which is sometimes like where I'm actually not the expert, or plugins, because you'll see that there is a lot of additional codes around SOFA. And for sure, since I did not implement them, I won't be the expert of this method or this method. So actually, this course is also to give you the right pointers. And anytime you'll have a question about who developed that, or is this kind of code or model existing somewhere, you can always get in touch with us. So you have my my professional emails. You can directly contact me. But for anyone else, they can also like go on the SOFA website and contact us through the contact form, and just let us know about what you'd like to do, who you'd like to contact later on. So usually, we make usually a roundtable, but I'll make that very short because sometimes it takes a bit of time. But so Nurul was maybe supposed to join us today. We'll see if he's joining later on the session. But we are three of us for this training session. Guillaume from Oticon, more interested on I would say ear simulation, ear surgery simulation. Ronak, you're working at Infintech 3D, which is the consulting company around SOFA. So you're just starting, right? So it will be to bring you all the, I would say, the most important information about SOFA and to get started with SOFA. And Carolina, you're working with Stefan, if I'm right, in Chile, and you will be working, I guess, on soft robots as well, and maybe for sensing, just like Stefan was also doing. So using soft robotics also for having some kind of sense and interactions with the environment. So regarding your background, so now we are actually asking in advance about the background so that we also can stress more or less different kind of points, technical points in the presentation, so that we know, we have an idea of what you would know, what you actually would not know as a theoretical background, and spend a bit more time on that during the training. Okay. So, as you might have noticed, SOFA is like no commercial product. It's a product which is rising from research and still used massively in the academic world. It started back in 2006, so we were all either very young, maybe for you two, Ronak and Carolina. Guillaume and I, maybe we were like already starting to get working, but was just the beginning. So yeah, that was the idea of three different research teams at INRIA, but really three separate teams that needed a common background, a common platform to build and make their simulations, but actually for different purposes. Some of them were medical oriented, some of them were more gaming, computer graphics oriented. So SOFA is a bit of a mix between, I would say, mechanical simulation, oriented a lot towards medical simulation, computer graphics. And now you'll see that there is another field like robotics, which has grown significantly. So it's something which is a bit unusual also in its lexicography, in the vocabulary that we use. Sometimes we talk like mechanical engineers, sometimes like computer graphics. So it depends. We are a bit in between. But what really was at the beginning of SOFA was this idea of having one platform to collaborate between different research teams. And if I could actually just give you a hint about why using SOFA rather than any other, either commercial or other open source solutions, there is one keyword that would actually summarize what SOFA brings. I would say brings more than other softwares. It's the keyword interactivity. The idea is having biomechanical simulation, mechanical simulation, but with which you could interact with many different ways. But we'll see that. The important aspect of SOFA is really this interactivity that we bring in the simulation. So what is SOFA? A physics engine, meaning a software that will mimic the mechanics of object. And when I say the mechanics, it's not only the mechanics of one object deforming or moving, but also the interaction of this object against its environment or against other objects, themselves rigid or deformable. Okay, that's this idea. So having soft and rigid body dynamics algorithms will have solvers and that kind of, all those kind of methods, collision pipeline and so on. But the core of SOFA is really soft and rigid body dynamics with interactions. And it has been used, as I said, for various purposes. Since the very beginning, medical simulation has been a really main purpose of the community. As I said also, in the early days of SOFA, animation, computer graphics, a bit of biology, but more recently, I would say 60, a big 60 of the community, even maybe 70 now, is really oriented towards soft robotics, sometimes applied on medical applications, but soft robotics and robotics with a robot that can interact with a deformable environment. So we extended SOFA to robotics, and it's a trend that will continue in the next years. So the concept of SOFA, since the beginning, is having a platform that can be shared among a community, but that will allow to make interactive mechanical simulation in a way that we can easily and efficiently design the simulation. Like in a few lines, I would say maximum 30 lines, we can define an object, its property, the way it interacts with other objects, and so on. So what we call a flexible design. Secondly, we wanted to have a software on the really software part, on the architecture part, which is following an open core model, which means that you have a core of software, which is open source. And around this core, you'll have separate repositories, which contain additional codes, additional features, which are implemented in these repositories that are called plugins. And we'll see that those codes, if this is like Ronac's code at Intech Ready or yours, Guillaume, or yours, Carolina's, it's definitely your code, the one of your institution, and you'll do whatever you want with this code. And finally, for having this interactivity that I mentioned before, we'll have to bring the simulation to a level that has sufficient efficiency, so to run sufficiently fast using multi-threading, GPU, and other kind of methods, so that the simulation can reach an interactive level. What I called before interactivity, I'm thinking about something which I think comes straight, straight in mind, which would be having a user that will in some way interact with the virtual world, like using haptic devices or even just the mouse, right? Or keyboards, interactions, whatever. So that kind of user interactions, we wanted to allow them with SOFA. But the fact to have an efficient simulation and a simulation with which you can also like interrogate about some state, some properties, some information about the state of the object, we will be able to include SOFA into some optimization loop or learning process like deep learning or reinforcement learning. You can use simulation that will manage also what we call dynamic simulation updates. I would also like include in that dynamic topological changes, a cut, element removal, that kind of thing. So basically a change in the topology, in the geometry potentially of your object. So having a simulation that is interactive at every level possible. That's what we wanted as a concept for SOFA, and that's what SOFA offers actually today. So about the code structure, open core. So as I said before, the core of SOFA, it's the base of SOFA, the base of code of SOFA, which is entirely written in C++, and which is under a license called LGPL. And LGPL, I don't know who is actually among you guys familiar with licenses in general and open source licenses. Are you? Like maybe Guillaume, I would know.
No, not at all.
So you have actually plenty of various open source licenses with various with various constraints, or some of them have actually no constraint at all. They all define how actually you can use, possibly modify, and possibly, if it's allowed, use internally and sell possibly this software yourself, or reuse this software yourself. That's what will define the license. LGPL, it means that you can actually download the software, you can use the software, you can modify the software yourself, you can even sell the software yourself. The idea, and integrate possibly so far within some products, but the philosophy which is behind is that if you modify the very core of SOFA, so the piece of codes that everybody has access to, what we expect is that if you change and improve one of those existing code, you provide this change, this fix, this correction, this small improvement back to the core of SOFA. If you implement a new method, this is your code. This is not SOFA, this is a SOFA plugin. It belongs to you, and you're up to define the license that comes with it. So that's what we call the plugin, those additional codes which can be implemented in separate repositories. Those ones, they are implemented by independent developers, companies, researchers. They can be open or private. They have any license that the author and its institution actually decided to put on this code, but SOFA and the whole community has nothing to say about them. The only thing is that we would be super happy actually to promote them, because we like to display that what people achieve with SOFA, the various kind of plugins that people develop with SOFA. So that's more of the philosophy of SOFA, sharing everything which can be shared, especially about the core. And for the rest, you decide what you want to do with your development, with your codes. I said before C++, but now coming directly with SOFA, when you download it, there is Python bindings. So it's some kind of a layer on top of SOFA that will allow you to use, it's actually an interface for Python, that will allow you to use SOFA, either using a Python script, defining your simulation using a Python script, but even better, to actually use SOFA, run SOFA simulation from a classical Python environment. That's actually something which is pretty convenient. Because as soon as you do that, you can use SOFA as any Python libraries, and you can then, in your whole process of Python scripts, include SOFA, maybe use some mesher before, create a mesh, give it to SOFA, run a simulation, export the data from SOFA, reuse them, analyze them, restart another simulation, whatever. That's really, then it's, I would say, limitless. I hope I will convince you about this limitless. All those possibilities offered by the Python bindings. Welcome, Nuru. Another information about SOFA is that it's cross-platform. So currently, for the binary version of SOFA, we are working on signing binaries on macOS, because macOS is becoming more and more constrained on the way to distribute executable on macOS. So we are working on signing the released version of SOFA, but where it's definitely super smooth, it's Windows and Linux. And for building SOFA, it works on obviously all the platforms. Documentation, we will see that right now together, but documentation, you can find that online. Everything can be accessed from the SOFA website. And there will be a user documentation, a developer, what I call API. So it's for the interface, code interface of SOFA, the API of SOFA, the developer documentation for SOFA. And as soon as you have any question relying or related to SOFA, there is the GitHub discussion forum where you go on the GitHub account of SOFA. There will be an area for discussion. Basically, it's a forum where anyone with a GitHub account can ask any questions that he or she like about SOFA, and we would reply there. So let me just make a short tour. Maybe I can do that here, and I'll get back to the slide there. All right, can you still see I'm right now highlighting the SOFA website. I guess you should be able to see it, right?
Yeah, we can see it.
Cool. Let me know if it's too small. I could zoom in if you need it. So that's the SOFA website for documentation. You'll find it always in community. Either you have the user documentation that will bring you here, and you'll have all the information on how to use the binaries, like the precompiled version of SOFA, how to build SOFA on your own machine from the source code. There will be some video tutorial and also how to use SOFA and with its main principles. All that, we're going to cover that together today. And these are additional pages that you could go to, read through, maybe with the training of today, plus the reading of those pages, it would help you like to get the whole picture of SOFA. But that's for the user documentation. And for developer documentation, you have a page called API documentation. And if you go there, I will click here, it will bring you to a documentation, a Doxygen documentation. So a documentation which is automatically generated from the code. And this documentation generated from the code, therefore, will be very code-oriented. If I'm interested to check whether, for instance, I'm looking for a mass component, here I will have various information about the mass. And if I'm looking for a specific mass, let's say a mass called the uniform mass here, I have access to the class uniform mass that will bring me here on the, here it was the constructor, but it's really the C++ code, which is some kind of explain highlighted. Here we will see that is actually the parameters that we call the data of this C++ code, and the whole inheritance graph of the C++ code. But that's really for more, I would say, C++ developers. If you are interested to get to understand what does this class, where does this class come from, and also what are the parameters of this component. Okay. So let's go back here and there. And so that's for the two documentation. And if you're looking for the forum of SOFA, it's also available directly here with forum. It will actually bring you directly on GitHub. GitHub, you can see it's the main account is SOFA framework. It's for the main project, SOFA framework. And then the code of SOFA is under SOFA framework/SOFA. You can see that here as well, SOFA framework/SOFA. And here you have an area for discussion, basically asking questions. You have various areas where you can ask any question you would like. So even people are sharing ideas sometimes, sharing some achievements. So like never hesitate to use it to highlight your own work. All right. So it's been 17 years now that SOFA is active. Among those 17 years, it spread over the globe. Actually, it took 3-4 years before SOFA crossed really the France borders, and very quickly with European project and international projects, SOFA started to go from a place to another, and now it's being used a bit worldwide, as you can notice from the map. And from the percentages as well, as you can notice, still very academic oriented. We are like every year we confirm those kind of proportions. 80% of the community is academic, and then the rest will be industrial with startups, with companies. Really, some of them are like industrial groups, and some of them are medium-sized companies, and we have also independent developers. It's like the smallest percentage, but it's actually one of the main percentage as well. Why? Because it's, I don't know if you can see that or from those percentages, but it builds some kind of a continuum from research to like international industrial groups. We have like a continuum from the independent developers, consulting companies. There is like PMEs, SMEs, and then industry, I would say, usual big groups. So it allows SOFA to collaborate at every level. If you are interested to collaborate with a research team, it would be possible. With another research team, if you are yourself academic, it's possible. And to get connected to more companies or whatever, it's always possible. So if you have any question, never hesitate to get in touch with us. In the last now it's, I would say, maybe 12, 13 years, there have been seven companies. And this year we have +2, so it's now 9 companies that have been or are being created around SOFA, which prove one thing, which is even if it's open source, there is no problem for making business or collaborating and so on, building your own technology, whether it's for academic purposes or for industrial purposes. So it will be the end of this, I would say, community sightseeing tour of SOFA. But due to the fact we had this community that enlarged among the years, that grew among the years, we had quickly a need to structure how things are actually working for the code and for the collaborations as well. And that's the reason why we started to build up this SOFA consortium. This consortium will be in charge of those 4 missions, making sure that there is actually no twice the same development, which is done on 2 different places without people knowing each other. If they don't want to collaborate, they don't want, but at least they know each other. And we always foster rather collaboration. We maintain the code for you guys, and we are releasing, fixing it on an everyday basis. We animate the community, try to support it as good as we can, and we structure, what I call structure the ecosystem is that we are organizing some kind of the governance of the project, how it is led, and we are having technical committees, we are having executive committees so that the project lives on and basically takes the good decisions. So that's what is done at this open source consortium. And for that, we have like partners supporting us and helping us. And the whole community obviously is contributing. You see here a few of the contributors of SOFA. And the way it works, and here it's important for you guys, because the way it works is that anyone can contribute to SOFA. So there would be possibly one limitation to that kind of things. Do you have an idea what could be a problem if anyone really could contribute to SOFA or push or change the code of SOFA? Any idea, Guillaume? It means that if anyone can make a change.
Excuse me.
I'm sorry?
Yeah, can you repeat, please?
Yeah, my question was, yeah, what do you see as a limitation if anyone could actually make a change within the source code of SOFA? Because that's the philosophy. The contribution is open to all. But what would be a limitation to such an open contribution process?
I suppose it doesn't have to break the previous version, at least.
Yeah, exactly. Yeah. It was the case, I would say, back in 2013, 14. There were actually almost no limitations preventing people to push something in SOFA. As soon as you had an account allowing you to do that, you could actually push something, and it directly arrived in the core of SOFA. And the change was some kind of available, but affecting as well everybody in the community. What we set up some years ago is that we set up a process of contributions where when you propose something, it's following a so-called pull request process. Ronak, Carolina, Nurul, are you maybe already familiar with that kind of process? Yes. Yeah, all right. So the idea is that people isolate the change that they propose in some specific so-called branch version of SOFA, and they propose that back to the community. But before it gets into SOFA, there will be a review process of this contribution by the core developers. There is about 20 people identified that can actually go through the code and make some feedback to the contributors. But that allows what? That allows to have a higher code quality, because like myself, when I propose something to SOFA and to the community, I'll get feedback to improve my C++, to improve the way I implemented the feature, and so on and so forth. So you'll get feedback from other developers, and it will make sure that it does not break the code, because we have a whole continuous integration process, which is checking everything all the time. So checking the compilation, checking that there is no regression, checking that all the tests that are set up around SOFA are fulfilled. And then finally, when it meets all the all the requirements, it will be merged into SOFA. And like that, every 6 months, we have about like 300 pull requests going into the core of SOFA. I mentioned the continuous integration, checking, all the time what happens in SOFA when someone is changing SOFA. Related to that, we release SOFA every 6 months, a stable version of SOFA every 6 months, and we work on the stability and quality of the code. So this is the consortium, including some companies which are financially supporting us, and also the community that I mentioned before, which is supporting us, but not financially, but through the code, through code contributions. So that matters as well to us. All right, that's for, I would say, the community tour of SOFA. Just 2 small videos to take some rest. You can see on the left-hand side, we have a video. It's actually now it's been 6-7 years that it has been made. An integration of a SOFA simulation. It's even CUDA based. It's a GPU version of a SOFA simulation, but where the rendering is performed within Unreal Engine. And so it's performed by Infidec 3. It was performed by Infidec 3D, which is the consulting company around SOFA. So they are offering a technical support and tailored development around and based on SOFA. On the right-hand side, it's a simulator that was made in 2015 for aneurysm clipping. It was a prototype, actually, a prototype simulation. All the graphics and so on were actually really not pushed at their best, but it was a proof of concept pushed by Insimo in collaboration with the research team back in already 8 years ago, and where we have like an aneurysm clipping. You see here it's an aneurysm, like a bag of blood in the brain that you need to identify, find, clip, and remove. That was the purpose of the simulation. So, and Insimo is a company developing medical simulators based on SOFA. All right. We start slowly to get into SOFA. I guess there is no question. I mean, if you have any question on this community part, do not hesitate. Otherwise, I'll continue here. All right. So let's get started. 2 ways to get started with SOFA. Either you download the binaries, or you download the sources, and then you'll have to compile the sources to have an executable version on your machine. Can you let me know, guys, what version you got? Guillaume, you got the binaries, I'm pretty sure. Ronak, Carolina, can you tell me, or you can also write in the chat what version of SOFA you do have installed on your machine?
I took the binary version 2.
I'm sorry, I can't hear you very well.
I took the binary version 2.
Okay. Carolina? Same? Okay. Okay, so just so that you know, who already compiled a software, any kind of software? No? You can raise the hand if you did. Okay. No one? Okay. So that's actually the reason why we distribute those binary versions, because some guys, myself, before going to SOFA, I just never compiled any kind of software. I could not really even understand what it meant to compile the software. So no worries. The idea is the binaries are there for that. We pre-compiled for you SOFA. So it means we took the code, the source code of SOFA. We compiled it on a Windows machine, on a Mac machine, macOS machine, and Linux distribution. And then we saved those and we provide those pre-compiled version for you guys. That's what we call the binaries. Those ones, they are released, as I said, every 6 months, like in a few weeks, actually. Maybe it might be like very early January. We will release the 23.12, meaning, so it's every 6 months. The last one was in 2023 June, so 23.06. The next one is 23.12, and then the next one will be 24.06, and so on and so forth. So they will be regularly released, and there will be obviously changes. I mean, we are changing the code all the time. So when a new version comes of SOFA, and if you upgrade your SOFA version, and if you have some plugins coming with it of yours, you'll have maybe to update those plugins so that they remain compatible with the latest version of SOFA. And for that, we are here to help, all right? If you have a plugin that you are compiling yourself, that you are developing yourself, obviously we will be here to help. If you are using, I would say, known plugins, especially the ones that are officially supported by the SOFA consortium, those ones, they are usually provided directly within the binaries of SOFA, including GOSA for BIM model, including, I don't know, like BIM adapter, which is also for BIM models, including some medical imaging, manipulation of medical images, that kind of things. We have plenty of, I would say about 20 plugins that we do ship with SOFA as well. The list is on the download page of SOFA. You can actually see that here. Let me show that to you, SOFA. Here you go on the download page. That's where always the regular stable binary version of SOFA is available. And if you want to check which plugins are available, they're here. That's all the plugins compiled and provided on top of what is by default in SOFA. So this list is updated from a release to another. So just make sure that you can keep an eye on this list sometime. All right, to compile it, if sometime you want to compile it, there is an online documentation to step-by-step accompany you for the compilation. And if you have an issue, the forum is there for you guys. What's the advantage of using the sources? Ronak, do you have an idea? I guess, what would be the advantage of using the sources and compile them, and what would be the advantage of using the binaries?
Binaries is already compiled.
Can you speak a bit louder? Sorry.
Yeah, so I'm not sure. You hear me now?
I'm sorry. I don't hear you very well. Carolina, do you have any, like an idea of why using one or the other?
Well, at first, in my case, I download the binaries. Then Stefan told me that compile the source is better because the plugins we were using, well, Robotics. So he told me it's better because, well, as you said, as you told before.
Yeah. So the binaries, the main advantage of binaries is that yeah, exactly, Ronak. So they are already compiled, so you don't need to bother with the compilation step. So it should be on macOS. Again, there is some issues due to the signature of binaries, which is a nightmare on macOS. But apart from this detail, there basically you download it, you click, it works. The drawback is that if you want to have access to the source code, to see a bit the code, you'll have to either download it separately and navigate it separately, or you can also access it online, like going to the GitHub account of SOFA here. You'll have access to the sources, but you don't have, if you just check them here online, obviously you don't have them on your machine. And the advantage of having them on your machine is that first you can, when you are a bit used to the code and C++ and navigating in it, you can have access to it and maybe understand it a bit better. And you can obviously change it. and add features, and then make this so-called pull request, those contributions back to the code. If you are having binaries, the code is some kind of frozen, right? The code has been frozen, pre-compiled for you, and you can't change it. So that's the main difference. So it's good actually for today's session that to get started, having the binary version is obviously the easiest one because we'll get easily started running a SOFA simulation from scratch. So it's very good to get started. But what I usually say is that later on, if you want to get a bit deeper in the code, having the source version compiled can be of interest. If it's only on the user purpose, I would say a release version should be sufficient, definitely. But that's really open and up to anyone to choose. Thank you, Ronak, for detailing things in the chat. About the sources, I told you SOFA is open core. So the core of SOFA is open, right? Open somewhere, open on GitHub. GitHub is some kind of organization, website owned by Microsoft today, which allows us to here online upload a code, in that case, SOFA, and it will be the same for plugins. Many people are actually uploading their plugins on open or private repositories on GitHub or GitLab. And as you can notice, by default, when you open the GitHub repository of SOFA, you directly arrive here and you have the source code. And the way it works is that people can download the source code here using the clone or download button. I think, yeah, now it's here, clone, code, sorry. And you have here the link to clone it or to download the zip. And then for those who would be interested to later on work with SOFA, to make a contribution, what you need to do is that you create first a fork. So a fork is that here, that's the official repository of SOFA. But myself, I have a copy online of SOFA. This is my so-called fork. My fork of SOFA is, as you can notice, it's like, yeah, okay, this is normal, but I could synchronize my fork with SOFA to get the latest update. But you see, it's the source code of SOFA as well. But just that I some kind of copied some years ago. Why? Because actually, having this fork will allow me to create sometimes some changes and save them online without straight away saving that and pushing that into SOFA. It's some kind of intermediate repository before pushing that back to SOFA. And when I'm happy with something, like with a contribution, with a change, I put that in a so-called branch. Those branches, they're available here. That's the various kind of branches. For instance, here, I did a fix. So I isolate the fix in a branch. And then when I'm happy with it, I make a pull request. I create a pull request. And this creates, as soon as I create a pull request, it will arrive and appear on the main SOFA repository. Online, there will be a list of pull requests. Here we have about 50 open, so 49 open pull requests. So 49 proposals made by the community to change the source code of SOFA. And we need to manage them. And we manage them here with all the core developers. We use a lot all the tags to sort them, to classify them, and then for us and for the author to know what to do with it. Do we merge it? Do we reject it? Do we close it? Or do we expect some changes from the user, from the author? For instance, here, we can check that here. So it's a pull request offering some kind of enhancement, an improvement of SOFA. It's to review. So we have to read it. We have to evaluate it. And we make some feedback about it. That's what is done here. And it was hidden here, but as you can notice, there is some checks which are automatically done so that if something is wrong somewhere in the pull request, we have an alarm, a warning, which is that appears, and that will prevent us to merge it. For instance, here, I don't know if you can notice, there is a file which is conflicting. So meaning that the file of SOFA and this one have really conflicting versions, and GitHub, actually Git, the versioning system behind, does not know which version to choose. He's complaining, and he prevents me to merge it into SOFA. As long as this is not clarified, I cannot merge it. So there is a lot of safety, I would say, yeah, safety checks like that are done online, so that even core developers do not mess up with the software and the development process. So yeah, there is, so that picture what was taken at the time, we had like 88 star on GitHub. Now we have a bit more. I don't remember where it's actually located. Yeah, here. When you go on the default page of SOFA here, and here, yeah, like it's about 10 times more. So it's improving. It's getting better. Anyone with a GitHub account can obviously happily put a star on it. It does good to the project. So that's for the way we work with SOFA. And now I'm going to talk a bit about the code. You're going to see it's going to be pretty light, but how the code is actually organized. Also, what you can see here from the SOFA architecture is that when we arrive on the GitHub account of SOFA, what can you notice? There is some files here below. So I'm going to use the pointer here. Some files here. I can actually check them here. Some files, including, for instance, the so-called README. But I have also plenty of folders coming with it. Therefore, so it's not only one file or two files, or the code is not directly, I would say, the C++ code containing the mechanical models, all the algorithms is not directly here, but we organized it in an architecture that I will detail here. So what we have here, sorry, I made a mistake. I wanted to, yeah, it was the pointer. It's organized this way. We have in the root of SOFA, so at the base of SOFA, the main folder is this one here. I'm going to zoom in a bit so that you see that, I hope, a bit better. SOFA with an uppercase. In this folder, SOFA, you will find really the source code of the framework. And it's some kind of split in two parts. SOFA/framework. So if I click in SOFA here, framework and component. What is framework? So the SOFA/framework is containing all central elements of SOFA. It's what I like to call the skeleton of SOFA. In C++, we call that it's the API, but it's the set of abstract classes. Does anyone know what is an abstract class? Some of you guys are, you told me that you were not you had no experience with C++, so no worries. I do not expect an answer when you don't have background on that. But anyone like Ronak, I think you have a bit. Could you like give a short description of what would be an abstract class in C++? Or Carolina, if you have any idea. And just for the notice, so Ronak, your mic is working. You just need to get very close to the computer to speak. I think it works. It was working when you were actually coming close to the mic. Okay, so classes. You know, a class of C++. It's like some kind of an object, so-called an object. But in C++, there is the possibility to play with inheritance, héritage in French. This inheritance, it allows to create some very basic class and then to say, oh, I'm going to create a so-called child class that will inherit from this main class, from this from this so-called abstract class. And this abstract class, so the main one, the first one, maybe it does not define a lot of things, but it will say, oh, I don't know how things will be implemented, but they should implement two functions, maybe init, when the simulation is initialized, and compute, when we need to compute something. So it will define two functions, which will be empty, but marked with something which will enforce anyone that inherits from this class to implement it. So you are defining some kind the design of your C++ class. So all those abstract classes, they define which functions have to be implemented. For instance, if you are a mass component, insofar we have specific functions that will be called. How to know how to implement a mass? You inherit from a class which is called base mass. Base mass is an abstract class. It does not implement anything, but it will tell you what functions have to be implemented if you are a mass. It's some kind of a template, okay? It's some kind of explaining how should a C++ code that implements a mass, how should it be implemented? So what is in SOFA framework is this some kind of skeleton. It explains how SOFA is articulated somehow, how SOFA works, but it implements nothing. So if you're looking for some kind of a Spring model, or if you're looking for a specific solver, it's not here. SOFA framework is explaining how a force model should be implemented. But it's a generic way of description of a force. Same for a mass. Same for a solver, how a solver should be implemented. This is an abstract class, an abstract way of defining how things should be implemented, but I'm not implementing any of these. So basically, if you take SOFA framework, SOFA is naked and you just cannot do anything with it. Why? Because you do not have any implementation. But you need SOFA framework to explain how things are working, how this skeleton of SOFA is articulated. And then in SOFA/component, you have all the implementations. For instance, you have all the Spring models. You'll have the different kind of mass that you can use in SOFA. You will have linear elastic materials, hyper-elastic materials, that kind of things, okay? That's where all the actual models, algorithms, they will be implemented in SOFA/component. Okay, that's the big difference between the two, but that's the whole code of SOFA. Somehow, SOFA framework is the architecture, and SOFA component is the implementation. And we can find that here, SOFA, so in SOFA with the uppercase component, and SOFA/framework. Framework is the architecture, the skeleton, and component are the implementations. Let's take an example. If I want to check an implementation of a mass, as I said before, I will click on component. And I mean, if I'm looking for the code itself, SOFA/component, I will find a folder containing all the masses. The masses here, I've got the mostly 2, 3 most important mass of SOFA. Uniform mass, mesh matrix mass. Okay. If I'm looking for a Spring model or a more complicated model like a linear elasticity, you know, the Hooke's law, then I'll go into solid mechanics, because that's what we talk about. And here I have the choice between finite element method implementation, Spring implementation, and so on. A Spring, you'll have a set of Spring model. So you'll have linear Spring model, polynomial Spring model, that kind of things. And if I get back for the finite element method, I have the choice between elasticity, hyperelasticity, and so on. Okay? That's how it is sorted. But no worries, if you are looking for information, I would say as a user, always go check here first in the user documentation. And if something is missing, please complain on the forum. We would be happy to add a more more things on the documentation for you. And then there's two additional repositories, which are super important to get started. It's examples/component, because there you'll have a set of all the component of the examples available, and guess what? It's following the exact same architecture than for the code. So if I go for mass, again, I will find the associated examples for the three main masses of SOFA. Okay. Same for solid mechanics, should be around here, exactly. FEM, spring, and so on. Okay. So that should help a lot. This example folder should help a lot to find, if you don't know how to actually use in a simulation one of those components, you'll find an example of it in SOFA. Last, so this with these some kind of three first folders, this is the core of SOFA. For historical reason, we still have some optional codes, what I call plugins, but some of them are available directly in SOFA. But it's slowly, little by little, disappearing, because what we like now is to have those plugins having their own repository. It's cleaner, and it helps a lot in the way to maintain the code and to process all those codes. But some of them are still available here. So in applications, yeah, I'm in the right place, sorry. Oh, GitHub is a bit slow, sorry. Yeah, okay. So GitHub has some slowdown, sorry for that. We'll check that afterwards. And so that's for application/plugins. You'll find a set of folders, each of them corresponding to a plugin. Some of them will be for CUDA implementations of SOFA codes. So I don't know who is aware of what is CUDA. So GPU computing. Does that ring a bell to everybody? Who is not aware of GPU computing? You can raise the hand. No problem. No, everyone.
Okay. I know it, but I haven't used it.
Okay. Yeah. So yeah, it's basically versions of codes that will trigger GPU kernels, so pieces of codes that will run on a GPU, on the graphic cards of yours. So you see application, plugins, and here is the list of some plugins, really I insist, some plugins available in SOFA. So the one I was referring to is called SOFA CUDA here, for NVIDIA GPU cards having some codes of SOFA, which runs on the GPU. You have some carving, so to simulate carving, methods to compute for collision detection using distance grids. You have some stuff like that. We are currently working at either reintegrating it into the core of SOFA or externalizing those into external repositories. So that's an ongoing work. But for instance, this one, beam adapter, is actually not here. It's referring to a code, a plugin that we officially support in SOFA. If you go with the GitHub organization called SOFA Framework, so it's github.com/SOFA Framework, the code of SOFA is here. But we do not have only SOFA. We have additional codes like a new GUI, graphical user interface, a code for beam model, some scripts here for us, some solvers based on C-sparse, and so on and so forth. So you see, there is not only SOFA, but we have also additional plugins that we officially support here on the official account of SOFA. That's for some other plugins. Okay. Maybe you may ask, but damn it, I don't get where can I find all the plugins? Where can I know about the various kind of interesting plugins? You can go here in applications, application plugins. You have a web page listing, I would say, for everyone, where it's explained how it works and so on. All the interesting plugins that we know If you have one, please let us know. We would happily add them on the list. So the ones that are officially distributed on the release version of so far, the one for rendering, the one for haptics, the one for performances, the one for robotics, and so on and so forth. Okay, so that's another source of information, application plugins. All right. So as so I won't go into detail on how to compile so far. It does not make sense, I think, for us today, but that's the 3 steps to fulfill. And everything is explained in the documentation online. Again, the user documentation, if we go here, user documentation, getting started, build, and we have for Linux, macOS, and Windows, the instructions on how to build SOFA. Today, we'll use the 23.06 release version of SOFA. And when we will start SOFA, we'll see the so-called GUI, graphical user interface of SOFA. Who already opened it? Just for me to check who already double-click on the, okay, Guillaume, Ronak, okay, perfect, everyone, great. Thanks, guys. So this is the current graphical user interface. We're working on a new one, a simpler one, and also like more modern one. We are working also on a new default example of SOFA, because as you can notice, this one, it's like a snake around a caduceus. The purpose was to give a sense of medical, but actually now SOFA is not anymore only focusing on medical. So we'd like to make something a bit more generic, a bit more also, I would say, trendy in what we highlight, because SOFA is able to do plenty different stuff. And the example here is a pretty basic one, and we would like to show a bit more in the default example of SOFA that will soon be updated. Now we'll get the important stuff. Okay. Do you guys need a coffee break, like 5-minute break, or can we continue up to, yeah, no, I see the Guillaume's face seems to say it's fine, or is that correct? Or
a cup of tea would be fine for me.
Oh, okay. So what we can do is maybe like make a 5-minute break. I don't have the clock under the eye, but 5 minutes break. Yeah. What will come right after will be we'll check the main principles, what is written here. What I also say, what I define as main principle is actually the features of SOFA, which are specific to SOFA, like some things which are available and implemented on SOFA that you will not find in other software. Not that they are better or whatever, or more exotic, just it's something which is really specific to SOFA. You'll see that there is 3 of them. It will be very important to like save them, keep them in mind for the user tutorial. And then we'll check some other features of SOFA, which are, I would say, more generic to any physics engine that you would find. But I will really insist on those 3 main specific features of SOFA, and then we'll go through more generic ones. Then it will be the end of the first part, and we'll move to the user tutorial. All right? So see you in about 5 minutes, like exactly 5 minutes, let's say that. I'll keep my video open, and then I'll activate my mic again so that we can get restarted. Okay?
Okay, see you in 5.
See you there. See you in 5 minutes. Okay, perfect. Let's get restarted. As I said just earlier, so what I call here the main principles will be the specific features of SOFA, which are available and implemented in SOFA, which are specific to SOFA, but not necessarily better or whatever. It's just like a design that has been chosen in SOFA, and a design that is important to keep in mind when we we'll look at a simulation or even build our own simulation. So there is three of them, three specific features of SOFA. And the first one is about how to design a simulation, how the simulation is described somehow. The simulation is described in SOFA as a so-called direct acyclic graph, basically a graph where you have a starting point called, we call it the root node. And from this starting point, we'll have subnodes, and each subnode will correspond to an object. And inside this subnode, there will be components that will describe and define what? The properties of this object. For instance, here, the subnode snake does correspond to an object, single object snake. And inside it, we'll have its discretization in space, so the mesh, basically, the numerical tools that we will use to solve it, the linear solver, the integration scheme. We'll get back to everything what I'm saying here, no worries, but we'll have here a mechanical object. You will see that the mechanical object is a key component in SOFA because it's storing the state vectors. So basically, the state of your object, in our case, in mechanics, the degrees of freedom, it will be the position x, y, z, if we talk about a deformable object in 3D. And the physics, the mass, obviously, of the object, and possibly, if it deforms, some internal forces, so some material law to explain how it deforms, and possibly some external forces applied to this object. If I have another object, another child node, just like snake, aside you would have, another subnode. All right. So a bit of lexicography here. So the entry point of the simulation, we call that the root node. I already said it. The root node will have child nodes corresponding, each of them, to an object. In this child node, we will have here, each of these lines is what we call a component. But this component is nothing else than a C++ class, right? The uniform mass is one code that we compiled and that can be used in the graph. And this component, if it's a mass, it has to follow the API. So basically, all the design, the way the skeleton of SOFA works, so to implement the proper functions, if it has to be a mass, it has to implement all the functions related to a mass. So all those lines here are a component, what we call that a component. And each of those components, they have properties, for instance, the total mass for a mass. And these kind of parameters, we call them the data in SOFA. And you will find that this vocabulary, this lexicography, you will find that in the documentation. And you will also find it in the code. We keep the same vocabulary in the documentation and also in the code. You will find some C++ variable, so some parameters, that are called data and the type of the variable. All this graph here is like this direct acyclic graph can be described either using a script in XML or using a Python script. We'll do both today in the user tutorial. So let's take the example of a lever. In that case, it's supposed to be a lever here. We have the root node. So we'll have a child node for this object lever. And inside this child node lever, we're going to have components that will define first one that will contain the DOF for degrees of freedom. In mechanics, it's always the position of our object. And we'll have also the derivative in time, so the velocity of our object. Possibly some other matrices and stuff like that that can be stored and associated to the mechanical object. But the ones that are important are the states, the degrees of freedom, We'll have other components like FF stands for force field. And those forces, they can be some external forces. For instance, a pressure applied or whatever. But it can also be what we call in continuum mechanics internal forces. It's actually the material of your object. The material, it's an equation that will define somehow how your object will deform, if it's a deformable object, following a law, an equation that relates usually the density of force and the density of deformation. And if you deform it, it creates internal forces. And if you apply forces, it will introduce deformation. That's the idea of a deformable model, or what we call in mechanics, a constitutive mechanical law, a constitutive law, a material law. M stands for a mass, sometimes coming from a mass density, or if it's just a few nodes, we can define some nodal mass. So, but we need some mass information. And we need some numerical tools to solve all that at each time step, right? So we will need a first thing, which is called an integration scheme. And so far, we also see the acronym ODE for ordinary differential equation solver. Does anyone know what is an integration scheme? Raising the hand. All right, we will cover that a bit later on. The integration scheme will typically be a numerical tool that will explain us how to go from the current time step to the next one. If I want to say that in a very simple word, but a bit more complex way, we will see that the integration scheme defines we will build at each time step a linear matrix system, A matrix, X vector, which is unknown that we want to find, our new positions, actually in SOFA it will be our new velocities, and B, a vector containing forces and so on. And what defines the integration scheme is what is inside the A matrix and what is inside the B vector, so that we find AX equal B. We can solve that. Who solves AX equal B? A linear solver, solving a linear system. Okay, so we have two kinds of solvers. The one solving things in time, and when I say solving things in time, you can just think what goes in A, what goes in B, AX equal B. And for a linear solver, solving AX equal B, once we know what goes in A, what goes in B. Okay. We will cover that again this afternoon, no worries. But what happens if we have another object? We create another child node aside. Under the root node, we will have another object, heart. It will have its own degrees of freedom, its own forces, its own mass, its own integration scheme, linear solver. Okay? And up to the number of objects you want to model. So in this case, it would look like that. We have in XML a root node. We open the node here, so we start the description of the graph here, but we have no backslash here because it's ending and closed down here. It opens here and it's closing here. So we open the root node, and inside the root node, we create another node. We put some components, which are, again, C++ classes. Those components will, each of them, be in charge of one thing in the simulation. Here, early implicit solver is an integration scheme, so it will define what goes in B, what goes in A, what goes in A, what goes in B. The linear solver solves this AX equal B problem. The mechanical object is a passive object, computes nothing, but it stores all the states variable, all the state information, and then the physics, the mass, the forces, and so on. We close the node lever, and if we want to have another object, we just create another subnode, heart, and so on. This, typically, we will do that step by step together with the user tutorial. In Python, and we will cover that deeper later on again, it looks, and just looks, a bit different, but it's the same. It's the very, very, very same. In Python, when using so far through Python, we will have to define one function called create scene that will define what has to be put in the scene graph when creating the simulation. And we have here as input the root node. So we take the root node and we can define what is that dt here, the delta of time. It's the amount of time that we do at each time step. You know, when we compute a simulation, we will actually decompose time into some sub-step of time. This is the amount of time that we compute at each time step. Gravity, if we want to apply some gravity to the entire simulation, so if we define that here, it will affect all the objects in the scene. And as soon as we have the root node, we can create a child node, and inside this child node, add objects. So it's exactly the same as before, just it's a different way of writing it, okay? But on the background, it's the very same, which is built once in XML, there. The second one in Python. In the tutorial, we will start with XML, just because I'm old, and I started with XML years ago, but no, more seriously, because XML is not indentation sensitive. So I can use indentation to really here make things easy to read. And really here we see we have two blocks of code, so basically two objects in the simulation. In Python, you cannot play with indentation because it does have a meaning in Python, so we can't play with indentation. All right. So that's the first main principle, the fact that we work and define a simulation which is described by a graph. The second main specific features of SOFA is on the screen, right in the middle of the screen. It's the fact that we need in SOFA a so-called animation loop. The name, but I'm biased, is quite clear. It's in charge of the loop of animation, the loop of simulation, the cycle of what happens at each time step. The animation loop is basically a for loop. If you click on run, in SOFA we have a button called animate. It runs the simulation. The animation loop is triggered and it will loop. It will loop over what? Over time steps. The animation loop is the component defining what happens within one time step. What are the various steps to be computed within one time step? And when it's done, it restarts over and over again. What is important to know about the animation loop? Two things. What you need to pay attention to with the animation loop is which animation loop is it? In SOFA, we have two of them. And therefore, since there is two, they do not compute the same steps and not in the same order. Okay, so we have two different animation loops in SOFA. But remember always that the animation loop computes nothing. I already mentioned the mechanical object, which is computing nothing, but those are important components. It's computing nothing, but storing the degrees of freedom. The animation loop is computing nothing, but giving orders, saying within the time step number 10, okay, my name is animation loop one, you're supposed to do this, and then in second, you're supposed to compute that, and then time step is over and restart. It gives order, that's the so-called visitors. They are browsing the graph, sending the order, the information that we need to compute this or that. But the animation loop itself computes nothing. It just gives orders to others, to triggers, for instance, collision detection. But itself, it does not even know if there is some collision detection in the scene. It's just throwing an order. Then, solving the physics, it throws the order through a visitor. It gives the order, but itself has no idea if there is really all that is necessary to compute the physics, to solve the mechanics. So it's some kind of a blind chief orchestra, right? It's giving orders, but without knowing if there is an orchestra in front of it. For instance, we will see that there is one of the two animation loops, which is called the default animation loop. This one is actually created by default if you forget to add it in the scene graph. And it computes two things. It will give the order of detecting collision and then solving the mechanics. If there is a collision pipeline, very good. If there is none, it doesn't care. It just goes to the next step, which is solving the mechanics. And then, if there is someone to solve the mechanics, very nice. Otherwise, next time step. Okay, that's what does an animation loop. It gives orders to define each step within one time step. And the third and last specific feature of SOFA is the fact that in a SOFA simulation, when you have an object that you want to model, if you like, you can use one representation, one mesh, one space discretization for the mechanics, for the collision detection, and for the rendering. What does that mean? It means that you may use one mesh, so one space discretization, used for the mechanics. So it means the whole forces, integration, mass, and so on will be done and computed over this mesh, this discretization. But for detecting the collision, we're not going to use the same mesh, but maybe some other, maybe coarser, maybe finer, maybe completely different mesh, or slightly different mesh. Same for the rendering. If you'd like to have like a coarse mesh for the mechanics and a very smooth mesh for the rendering, you may do that. But what's the problem by doing that? It means you'll have several meshes. The mechanics will move, will deform. But you want, for instance, the rendering mesh to move accordingly. This is what does a mapping. A mapping is actually a transformation, a connection, if you like, that will allow you to connect the mechanics, for instance, with a rendering mesh. And when the mechanics will move, the position and the velocities at each node of the mechanics, each node of the mesh used for the mechanics, the discretization used for the mechanics, will be interpolated on the mesh used for the rendering so that the rendering mesh moves according to the mechanics. Same for the collision detection. So it looks somehow like that. We would have here a blue mesh, which, it's an example, but let's say that we have a tetrahedral blue mesh here, which is a bit coarse, And here, it's hard to see, but it's a fine triangulated mesh. So only triangles on the surface. There is nothing inside the mesh. It's only a surface. An envelope meshed used with triangles. maybe same for the rendering. But we want, when the mechanics is moving due to, I don't know, gravity that applies or a force that applies on our deformable object, we want this deformation to be propagated to the rendering model. Even if the mesh is a bit different, we want the deformation field, we want the motion, the position to be propagated. This is done by the mapping. The arrow here is the mapping. Okay, it's a transformation, it's a space transformation. Okay, we will get back to it. What is, on your opinion, do you have an idea what could be the interest of doing that? Of having the possibility, nothing is compulsory, you can use the same mesh for all three, but what is the interest of choosing the discretization of each part of the simulation, the mechanics, the collision detection, and the rendering? Any idea?
I think it depends on the simulation, how accurate it is or how fast is it.
Yeah, exactly. What it brings, this possibility to decouple those three representations. It's up to you to choose the level of refinement, of therefore accuracy, that you will put on the mechanics of the collision detection, the quality of the rendering. But obviously, the more accurate you will be, the slower the simulation will be. So basically, you choose what will be the trade-off on efficiency, performances versus accuracy. Okay, that's really up to you to choose those various aspects, decoupling the mechanics, the collision detection, and the rendering. The correspondence is always computed and ensured by the mappings. For instance, here we have a rendering mesh. It's only a surface mesh, like an envelope mesh made of triangles. You will see the triangles right now. In fact, the mechanics is not computed here. The mechanics is computed here on this volumetric, so really a volume mesh made of tetraedra, coarser. But when it moves, this surface red mesh, triangulated mesh, follows the deformation, the motion computed by this volumetric mechanical mesh. Okay, so the transformation, the mapping, is ensuring the correspondence, sorry, between the two. And to conclude this first part, we'll see now all the other features. To recall, three main specific features of SOFA: the scene graph, the animation loop, and the mapping. The scene graph, we organize the simulation and describe the simulation, the various objects and their properties as a graph, starting with a root node, child nodes. Inside each child node, we have components which have themselves data defining the properties of the object. The animation loop is in charge of what happens within one time step. And the mapping will allow us to use, possibly decouple, representations of one single object. And now, what I'm going to present is super generic to any other physics engine. Starting with the fact that we need, we'll get back to it, but insofar we use a lot finite element method. It's a numerical method which allows to compute a space integration of an equation. So it's basically the integral that you put on your equation. It's a method that will allow you to compute sometimes an approximation, sometimes it's going to be exact, but basically a space integration of the mechanical equation, or the mechanical equilibrium. But it is based on something very important. Actually, all the numerical methods are relying on that principle. We need to discretize. We discretize in time with time steps, and we discretize in space. Why? because it's impossible to find an exact solution on a random volume, on a random domain, as we say, if we want to use a mathematical vocabulary. If we make the integral over omega a random domain of the whole mechanical equation, we have no exact solution. We have no known solution of this equation, of this problem. To do so, we use a method which is called finite element method, which requires one thing, a space discretization. So that's the reason why we need always either a point cloud or a mesh. And in SOFA, we use a lot meshes because finite element method, we need elements, whether it's volumetric element, surface element, or 1D line elements. So for that, we need to load a topology. The topology, it's the discretization in space plus the information of connectivity. For instance, which triangle is connected to which triangle, which other triangles. What are the triangles surrounding one node, one vertex, and so on and so forth. That's the topology. And typically, when you make a rendering in Blender, you need a mesh. When you, typically for rendering purposes, that's another kind of cases where you need often this kind of discretization, space discretization, this kind of meshes. I often get the question, how do we generate meshes in SOFA? We don't. SOFA, it's a simulation toolkit, a simulation framework. There is meshing, some basic meshing simulation in SOFA, but best is always to use dedicated mesh tools. For instance, using Gmesh. Gmesh is one open source library that allows to create, even sometimes using parametric equations and sometimes, but yeah, you can generate a mesh, a 3D mesh, a 2D mesh of an object. Mesh Lab for meshing stuff. I don't have any personal interest in all those softwares. Just know that there is, it's a research field on its own, meshing, and there is plenty of solutions. We are pretty well connected to either Gmesh and also Seagal, which is a meshing library that we use a lot and which is actually implemented and developed at INRIA by some teams close to Hervé de Lingette, also at Sophia Antipolis, and also in Paris. So yeah, Gmesh, Seagal, up to you to find actually the mesh tool that suits you at best.
I have a question, Hugo.
Yeah, go ahead.
What would be the advantage of using a full object meshing versus Coursera, for example? So, as I understand, so Coursera is BIM models that avoid to mesh the full volume of your device or your object. What would be the advantage and drawback?
So it's a specific question that you are asking on. It's related to what is called BIM theory, la théorie des poutres in French. Who already heard about BIM models? No? Okay. So it's really related to finite element method for mechanics. In mechanical engineers are lazy. That's one of our best properties. We are lazy, therefore we try to simplify things as best, keeping the best performances and accuracy possible. Let's take the example of the top right image, which is the heart here. This heart, as you can notice, it has some kind of shape, which is nothing to be parametric, right? It's not like a function that can define this kind of shape. It's volumetric because it has cavities inside, but actually, I don't know if you know, but the heart is a muscle, actually a thick muscle in some areas. So it's a volumetric object. Obviously, it's a 3D object, but even the walls, they have a thickness, right? They have a thickness. So if we want to run a simulation of that, we cannot really simplify it using some lines or stuff like that. It's really a 3D model that we need to mesh and discretize in space with 3D elements. But it happens that regarding the geometry especially and the mechanical properties of some objects, we may be interested in simplifying the finite element method. So it's a bit of an aparté here to answer your question, Guillaume, but it's a generic question about finite element method. Let's take the case, not to go straight away on your application, Guillaume, to remain generic. Let's say that I want to run a cloth simulation, like, you know, garment, like simulate a t-shirt or a dress or whatever. What can you tell about like my shirt? It's particularly thin, very, very thin. Meaning that if I take a piece of, like a square of garment, un bout de tissu, a piece of garment, why would I bother to create a space discretization in the thickness of my object? It's almost like it's 1 millimeter or 2 millimeters. So basically I have one of my 3 dimensions which is neglectable regarding to the 2 other ones. If I put my square of garment on a plane, I have my square, okay, y, x, xy, but z can definitely be neglected. So in mechanics, it will be the same for instance, if you take a wire or an endoscope or a cochlear implant, it's something that looks way more like a wire, right? Like let's take this wire or just this piece here. In this case, my mechanical object has 2 dimensions which are neglectable, because finally I have something which is mainly a line. Maybe it has a thickness, a shape, some shape in the section. Okay. Guess what? Mechanical engineers thought about it. They optimized actually 3D models so that it either works on a plane, a 2D representation. It's actually called, I'm going to write that in the chat so that you can see that. Shell models, shell FEM, so shell finite element models are actually 2D models that are neglecting 1 dimension, but taking it into account. They just know that the thickness is very low. You can specify a thickness. It will be taken into account in the mechanical computation. So the whole fields of density of forces, how it deforms and so on, will take into account the mechanical properties, including the stiffness, but the mesh, the space discretization, is only a 2D mesh. Okay. The same for a wire. We will only use a line, a beam, that can deform in 3D, right? But its shape has no thickness. It has no section. The section will be integrated, the shape of the section, the thickness and so on, will be built in the mechanical model. It will be possibly, in what is implemented in COSRA is a linear elastic model, a linear elasticity, but just neglecting 2 dimensions and taking into account one specific kind of section. So there is the whole inertia term and so on, which are properly taken into account. It's not like a spring. It's really like a mechanical model, which is on the mesh, on the space discretization, simplifying it, but on the mechanics, keeping a very accurate modeling of your object. So now to get back to your question, Guillaume, when to use a 3D mesh, when to use a shell model, or when to use, I'm going to go up to the end, a beam model, it's really up to you to choose, but it's when 1 or 2, 1, then you go back to 2D, it's a shell, or 2 dimensions are being neglected, then you go to beam models. it's a line. Up to you to choose what model, what FEM model is most appropriate to your purpose. Okay. But again, when you have like such a case with a heart here, where the whole discretization, I mean, the whole geometry of my object is completely random. It has a thickness in all directions and so on. So I cannot neglect any of the 3 dimensions. I need to have a 3D mesh. Okay.
Okay, thank you.
Sorry for, I hope it was not too long for what you asked. But yeah, so COSRA is one of those implementation, and in 1D, it's a very, very good approximation for wires and wire-like structures. So for that, we need to load meshes in SOFA, and we have so-called mesh loaders to load that kind of space discretization. We will see them in the user tutorial. And if, for instance, for one single object, we want to have, you remember, we want to decouple the mechanics and the collision detection. So we will use maybe 2 different meshes. We will load 2 different meshes. We will have 2 mesh loaders loading 2 different meshes that we will use for the 2 different parts, for the mechanics first and for the collision detection second. Okay. And that's the mapping which is connecting the 2. In SOFA, you have also a collision pipeline. We will cover it in the user tutorial that comes by default when you get SOFA. It works always the same way, in 3 steps. Depending on how you count, can be 4. I like to say 3 steps. The first one is there is 2 steps in the detection, 1 step as a response. The detection starts with a so-called broad phase. It's simply checking whether objects which are getting close to another, are they possibly colliding or not? How does that work? They are actually, this broad phase is checking if the bounding box around each of those objects, I don't know if you can see well the white bounding boxes in the image. It's checking whether those boxes are intersecting or not. It's a way to actually quickly exit, because if the boxes are not intersecting, the check is super quick to be computed, and then it means no collision. If the boxes are not intersecting, it means the object for sure will never collide. They are not intersecting right now in this time step. But if the boxes are intersecting, it does not mean that there is collision, but that we need to check closer. We need to take a closer look. So that's the second step, the narrow phase. If the boxes are intersecting, we'll take a closer look in the narrow phase. And here, that's the second image below. We will check, for instance, if we know that the contact occurred in this region here, we will check along those triangles, triangle per triangle, which of the triangles are colliding possibly with the sphere. If there is one or several triangles here, those triangles or the sphere, we call that the collision primitives. It's the primitives that we use to detect collision. So we check one by one whether it's colliding with another. If not, no collision. If there is some collision, we will see some red lines. Here it's a green one, but then we will see a red line appearing when there will be a collision. And it will create a response. Which kind of response? There is actually several ways of responding to collision. So first, detection. We check broadly whether boxes are intersecting or not. If they do, we check closer with the narrow phase, and we use this proximity intersection. We will see actually this kind of component in the scene graph. We'll see something called intersection, which checks what? It's a method checking primitives per primitives. Are they intersecting or not? For instance, is the sphere through the triangle or not. That's what it means. And finally, if there is a contact, there will be the detection will actually create a detection output used in a third and last step, which is a response. There is different methods for neurophase, for collision response. They are listed here. For the collision response, know that there is mostly two of them. Either we will respond to collision using penalties. It means we will check how the objects are through another. There is an interpenetration. We take the interpenetration distance and we will penalize it. We will apply a correction factor and apply a force based on that, some kind of a spring force. And the other method is a more complex approach where we don't apply a force straight away, but we will try to solve a second system, so-called a constraint problem, a constraint system, in order to find the exact forces, taking into account the property of the object 1 and the object 2 that are intersecting, to find the exact forces satisfying the fact that the objects are not colliding or actually not intersecting anymore at the end of the time step. So that's two different methods. This one is actually, as it is implemented in SOFA, a pretty simple one, but we will see that it can also be a pretty cumbersome to tune and possibly unstable one. That's the drawback. This one is more computationally demanding, but more stable. We'll take a look again on those two. And then that's for the core of SOFA. That's more or less the features you'll have as well in SOFA. You'll have different mechanical models. I already mentioned, we covered, browsing in the code. We have some springs. We have mass that can be computed over the whole volume of the mesh. We have finite element-based constitutive law, like finite element, like linear elasticity. The constitutive law, the way the object will deform. We have solvers, as I said, integration scheme to detail how to build the AX equal B system, to go to the next time step, to find the solution at the next time step, and linear solvers to actually solve this linear problem. So all that is available in SOFA. And around it, you have plenty of plugins. The idea of those plugins is that they can be, as I said, tailored. Some of them are officially supported by the community, by the SOFA consortium. But some of them are open, but just implemented by some guys around SOFA. Some of them are private. Some of them are really kept private by some companies or sold sometimes by some companies. So a lot of them. Anytime you're interested in a new feature which is not existing in SOFA, do not hesitate to contact us, whether it's existing already or not, because there is like more than 100 of plugins available around SOFA. One of them being, for instance, coupling SOFA with Python, which will allow you to run simulation, describe a simulation without C++ skills. We'll see that it allows to have a lot of interactivity within the simulation. It has a dedicated repository. It's a plugin. It has its own repository, this one, SOFA Python 3. But SOFA Python 3 is provided by default when you download SOFA, whether it's the sources or the binaries. An example, it's a very old example actually that I did years and years ago back with SOFA. It was when Python just arrived in SOFA. I was using medical images here from a patient that had a kidney tumor that you can see in blue here, down the kidney. And the idea is that before in SOFA, we could only define, okay, you have 3 needles here, 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 and I will run my simulation, and that's it. The big change with Python was first change with SOFA, with SOFA Python, so the use of SOFA in a Python environment, was that we can access to the SOFA simulation. Therefore, we can request some information, access some information, even more, create or destroy, but here create new objects. Here, this third needle was actually not planned at the beginning. And dynamically, you can create new object, you can make some object disappear, and so on. So this interactivity, very high interactivity, is brought through Python. Because we can really, through Python, have access to SOFA and play with the simulation graph of SOFA. We will play with it together. SOFA CUDA, I already mentioned it. So it's a GPU versions of some codes of SOFA. We are currently working at actually updating this plugin so that most and possibly all the simulation could be could be actually run on the graphical processing unit of your computer, so that it's actually accelerated at its maximum. And yeah, the way it works is it's actually that it's changing almost nothing from your simulation. We'll see that only some keywords are changing. Instead of working with like v23.06, we add some prefix specifying that it's CUDA, and it automatically activates part of the GPU versions of SOFA. But yeah, we are still working on it to release a better version of SOFA CUDA currently. So plenty of plugins, including also coupling the simulation with haptic interfaces. Among those, the one we like pretty much is like a Swedish company that we like to work with is Follow, making tailored haptic devices, super cool. Appli Robotics, the same, doing like also portative haptic interface that really allows to have a user interacting with a simulation. So here it's a Geomagic, it's the Geomagic devices that you see here, a bit cumbersome to use. They're a bit big, those haptic devices, but anyway, that allows you or a user to run a simulation and to interact with it while it's running. So, as I said, and I'll say that again, there is really a lot of them, a lot of those additional features around SOFA. They are not all yet integrated into SOFA, first because they are not all at the same level of quality, the same level of documentation, the same level of use. And some of them also are sometimes, part of SOFA are sometimes externalized outside from SOFA if they become old, for instance, and they become plugins as well. So SOFA Python, integrating SOFA within rendering engine, Unity 3D, and Unreal Engine, which is, it's actually something which is done by our consulting company Infintech 3D, where you will be working on that. Medical images manipulation, model reduction. So there is plenty of ways to also improve the performances of your simulation. There is about that a dedicated page on the SOFA web page. I could show you that later. On the user documentation of SOFA, you have a page about performances, soft robotics, BIM models, and so on. So the whole plugin list, as I told you already, is available online. And never hesitate for requesting access, and also requesting whether this or this model, method, algorithm already exists somewhere and can be accessed, to avoid getting started and implementing it yourself if it already exists somewhere else. As a reminder, all the code you're going to implement and create yourself in your plugins is yours. Okay, so feel free to develop it. We cannot, or I mean, we have some consulting company again that can do that kind of services, that can offer support on your private codes. But what does more the consortium is to focus as much as possible on the open source part, which is already a lot. So we focus on that. But yeah, you're completely free then to create your own code and define and do whatever you want with your SOFA plugins. Today, we're going to together start to implement our first simulation, building a simulation step by step. But for later on, really never forget that the community, me included, we will be here for you through the forum for asking questions, user or developer questions, reporting bugs, contributing, obviously. There is the documentation as well, which is online. Something missing, please complain. We have, I would say, pretty few time actually to dedicate to documentation, but what does us a lot of good is to here users saying, hey guys, just provide us this documentation page. It's definitely missing. Then pushes us for improving the documentation for you. Obviously, we're available like on GitHub, but I don't want to move to X, so I let the Twitter logo, LinkedIn, and YouTube if you want to check out for videos of SOFA. I'll be always available for contacts if you want for information, whatever the information about SOFA. And the idea is that you take advantage of the community for job opportunities, for instance, for you, Carolina, later on, if you want to move across the world for finding another research team to work with or to collaborate or to make, I don't know, continue a career anywhere else, that's the role of the network of SOFA. If you're looking for recruiting, it's also a way of finding people to contact us. And basically participating to all the various events. We have weekly dev meeting, but more, I would say, maybe more of interest for you guys would be the twice a year, the technical committee that help us to define where to go on very technical point of SOFA, what kind of methods are missing, what should we improve in SOFA, what are the development ongoing in the research teams. And once a year, it was actually 3 weeks ago, so it's the community event where people are presenting what they do with SOFA, the SOFA week. So it's going to be again next year, second half of 2024. The agenda of SOFA is available online. It should be here, if I can find here. Here. Yeah, sorry. In events, agenda, I'll also update the agenda for 2024 in the coming days. I'm going to update this year. So that's all for 2023, as you can notice, but soon we're going to add a bit more. So that's for the first part. We're going to move to the user tutorial. And there we are going to reuse a lot what we saw just before about the 3 specific features: scene graph, AnimationLoop, and mappings. And as well about all the other features like the topologies and the collision pipeline, which is available in SOFA. Okay. Is there any question on your end?
Actually, yes, but I think I will keep it for later or for a focus discussion with Lille's team.
Okay, okay, or
intersection, collision, and reaction forces and so on. So,
okay.
Thanks for the main overview of the software.
So we'll move to the user tutorial. What matters really a lot. So first, always feel free to ask questions, especially in the user tutorial, because it's going to be really step by step. So everything that we'll see will base the next steps on what we just saw. So just if on the slide or on what I'm saying, there is something unclear, you just straight away stop me, request for an explanation, and I can, or re-explanation, there is no problem, can re-explain that, and I would happily do that. As you said, Guillaume, also for the future, even if you'll have all the materials for the session, but for the future, if you want to have a deeper understanding of something, just contact me. I would be happy to take some time. We're planning to hope, I guess, for 2024 to create more and more materials that we would like maybe to put online, even maybe videos of sessions on specific topics, so that people can really level up on, for instance, how does the collision detection work? What are the 2 different kinds of collision response? Why? When to use them? And so on. Because just to, and that's a very good reason to ask all the questions you're going to have in the next hours, because SOFA is at the bridge of many different fields. Computer science, so code, mechanics, mechanical engineering, sometimes a bit of robotics, that I'm actually very bad at. It's not my background, but robotics. Numerical analysis. When I say numerical analysis, it's what I said earlier about what is an integration scheme find the solution at the next time step. So therefore, to define what goes in the A matrix, what goes in the B vector, what kind of methods do exist to solve this kind of matrix linear problem. All that are actually full university courses or engineering courses. We have materials about all that that actually took a bit of time to set up, and some of them are actually set up by some research teams. We are happy to share them because basically the better you will become, the best the publication will be, the best the products will be, the quicker the products will be released. Basically, the more dynamic the community is. So that's definitely the kind of the kind of dynamic we want to set up, especially for 2024. I think we really want to go for, I would say, pedagogy, but also a high level of pedagogy, not like high level of. We don't pretend to have a high level of pedagogy, but to push people in terms of the level of scientific background that they have or they understand about what is going on with SOFA. That's something we want to push quite strongly in the next months and years. Sorry.
Yeah.
So yeah.
I think next step for me would be to go in detail with the Defrost team on the simulation we already have, and better understand what is they implement inside. And yeah, I will be happy next year to attend some of your next session.
We pre-organized like some weeks ago 2 sessions on, to give you an example, on model order reduction, which is a plugin around SOFA. The method is called model reduction, so it allows to reduce the complexity of a model. In other words, to make it faster, if I want to say that quicker. And it's actually a plugin which is not straightforward to use. The documentation is being significantly improved currently by the developer working on it. We did a first training session on it. I think we'll do more next year. And we would like to, again, push those information available to anyone. Same for soft robotics. So that's why I'm mentioning that, because I think for soft robotics, it was actually on COSRA, the one I'm thinking about. We did a COSRA training on the COSRA plugin BIM model applied for robotic application. We did a specific training some weeks ago. That's the kind of training we would like to generalize a bit and to ease the access to those trainings. Okay.
Okay.
So I think in the loop here, for at least for COSRA and all what is robotic oriented, I will keep you, Guillaume and Carolina in the loop, because you already mentioned that you were interested. I mean, that's your topic, Carolina, so definitely, and Guillaume definitely as well. And for you, Ronak, I think what could be of interest is also performances, some more insight about performances and biomechanics. I mean continuum mechanics. Finite element method. How does that really work? Because it links everything from the equation to the code. So everyone does not need to understand that part. We can like hide FEM under SOFA and say SOFA is doing that for us, which is good. But maybe for what you're doing could be of interest. So let us know when you are ready. The best is always this way. Let us know when you're ready, and then we arrange the session. And let us know a bit in advance, like a month in advance, so that we can arrange that properly. But yeah, I noticed the two interests already. All right. Do you need some other tea break? Like again, 5 minutes. The idea is to make short ones, just so that we keep a bit of time to.
Fine for me.
Yeah. Okay. So just let me check the time. Okay, like at 11:22 for the CT, like really 5 minutes. I think I'm gonna stay here, just maybe grab a glass of water and then come back here. But yeah, if you have any question in the meantime, either you can write it in the chat, or otherwise see you at 11:22. So 5 minutes in 5 minutes. So, all right.
Okay.
See you. So we will start the second part of the training of today. It will really be this step-by-step building of a simulation, where we'll start with an almost empty sofa simulation and add step-by-step object in the scene and starting defining the property of our object and so on and so forth. The idea of this user tutorial is also to face some specificity of sofa sometime, where you'll see that some stuff happened a bit like in your back. And the idea is to highlight them here so that you do not get astonished or surprised that, how does that happen or whatever. The idea is to highlight all those things that happened in a sofa simulation, and therefore to properly and entirely master the whole pipeline of one simulation step. Okay, that's the idea. So what you will need from here are the materials that I sent you per email. So it was a zip containing scene examples from 0 to 17. And you'll have to open Sofa as is, like running run Sofa, the executable of Sofa. Myself, I have it here. So you should still be able to see my screen and to see Sofa appearing. Let me know if you don't. And what I will have as well, and what you can do also on your end, is to, like in an editor, I'm going to zoom in a bit, file, open folder, and I will open the folder containing all the scene files so that I can open them one by one and see what is inside. You can do that as well on your own using any editor of your choice, but the idea will be to edit those files. Again, I'm using Sublime. You can use Gdit, or you can use really the file editor that you like. But the idea is that we will play with them, run those simulation files with Sofa, load them and run them, but possibly modify them as well, like typing a few things and see what it does in the simulation when we reload the whole simulation. Okay. So I'll let you the time to set this up. And so we did the overview of Sofa. We'll do the user tutorial, and this part we lighten it a bit, the simulation from math to the code. But I kept the part that what I find interesting is to really still take a very short look at the I would say API, the C++ code, which is running under the hood of Sofa, and so that we can uncover it slightly and just see how that's how it works. There is no magic under a button, and so that you understand the full cycle of one type step once again. So when you run Sofa, when you actually launch the executable called run Sofa, that's what you get: a graphical user interface that has here a 3D view, where if you mouse click left, you can rotate around it. If you mouse click right, you can like translate the view. And there is even here some buttons to here, so save the view if you like, or reset the initial view that you saved before. I'll take just a few minutes to explain what is here, what is available in the graphical user interface, because we'll use it a lot. We have here, okay, file open to open a scene file. In Sofa, we have two kinds of files, XML or Python. XML, it can be with an extension .xml, or in Sofa, we like also to write .scn for a scene file, a scene simulation file. SCN is XML, and otherwise Python will be PY. So we can open a file, it will load the simulation, and we can obviously reload it. It's actually just doing what? Taking the file and reloading it from scratch. And the time gets back to 0. Step 0, we really restart the entire simulation. In Edit, up here, we have what matters, firstly, a plugin manager. plugin manager, now we know what is a plugin. It's those optional codes, additional codes. Here, it's actually the additional codes and all basic, all dynamic libraries. What is a dynamic library? It's the result of the compilation of a plugin or a module of SOFA. So here we have all the features that you loaded in the executable. And we can see that some plugins are here, like Beam Adapter, which is in charge of modeling beam models using the Timoshenko beam theory. Some SOFA matrix for visualizing and making some matrix analysis. SOFA validation, so say image plugin, which is a moving, which is going to soon move into the image, just image plugin. The image plugin is a plugin in charge of medical image manipulation and image manipulation in general. So a list of all the plugins is available here. It's actually useful to have access to this plugin manager, because if sometimes someone tells you, hey, do you have Python loaded? Do you have your SOFA Python plugin well loaded? Here I can click and I can tell, no, it is not loaded. It should be here. It is not loaded. I will load it later on. I will show you later on how to load the plugin. It can be done here through the add button. Using the add button, you will load SO on Linux for a dynamic library, SO dynamic library, or on Windows, a DLL. You will load the DLL directly here. And when you load a plugin, suddenly you make all the features, all the code which is implemented in this plugin, you are making them available in your simulation. Okay, you can define what kind of mouse interaction you want, but yeah, that's not really of interest, and that's it. Then we have a panel which is in charge of simulation management, starting the simulation, calling animate, but it's running endlessly, so infinitely the simulation. Time steps are computed after time steps, and if I click again, it stops. The other one step is making one time step each time that I click on it. One time step, one simulation step. The amount of time that we are going forward at each time step is given here. It's the one which is given in the root node, dt, delta of time step. The button here, reload scene, is the same than this one here, reloading the whole simulation file. I disencourage you to use the real-time button, because it's actually something that will cheat on the time step and possibly lead to instabilities. It will enforce the simulation to be as fast as the real time. So that's what it does, but I really encourage you not to use it. I'm actually for removing it sometime. You can take screenshots. Actually, in the viewer widget down here, you have the list of shortcuts that you can use in SOFA. For instance, drawing some axis using the A key of the keyboard, or taking a screenshot with S. A button is available here as well, or recording a video, pushing the V button. Okay. But as soon as you take screenshot, or most importantly, take videos, it will slow down a lot the simulation, obviously, because you are exporting a lot of things all the time. So, but yeah, I'm going to use here a lot the A key for drawing the axis in the training. So the file edit here, the view, the buttons for running the simulation, and here we have a set of panels, mostly this one. Let's start with the graph and the view. That's graph and view are the two most important ones. Viewer being just shortcuts dedicated to the viewer here, QGL viewer that we're using here.
Excuse me, Hugo, can you zoom in a little bit so that we can have a better view? Yeah, okay, thanks. We can. We cannot hear you anymore.
I'm sorry, is that better? I mute myself.
Yeah, okay, thanks.
Great, cool. So we'll take a closer look to this view and graph widgets here. The view is obviously everything which is around rendering. It's to choose which layer of sofa, which part of your object you want to see. You remember? We said earlier, we can, if we want, decouple, use different discretization for the mechanics, for the rendering, and for the collision detection. Therefore, we need a way to visualize each of those parts, because we may want for debug or for analysis, we want to see how does look the mesh for collision detection, how does look the mesh for mechanics, and so on and so forth. So the visual models here is displaying all the rendering models. The one called force fields. So I'm gonna use the B key of my keyboard. I'm gonna use the B key of my keyboard to change the background. So here it's black, I'm turning it white, just so that we see that a bit better, but for what I want to show. So I will hide now the visual models, which are, remember, just models, a mesh, a discretization in space, used just for rendering, okay? So we'll hide it. What we see now is the mesh, or the space discretization. Here it's a sparse grid used for the mechanics. And in our case, we just have the snake, which is deformable. So that's the mechanics of the snake. You see, it's a very simple way of describing the mechanics. We are just like using a sparse grid around the snake and computing the mechanics, the mass, the external, internal forces applied to this object, and therefore how it deforms on this grid. So the mechanics is here, force field. And last but not least, the collision detection. So I'm going to hide here and get back to black. So the collision detection, that's the mesh, that are the primitives which will be used when we want to detect if there is collision or not. If I get closer here, you can notice it's a triangulated mesh. Here for the caduceus, we have triangles here and a line as well in the middle for the bar of caduceus. So we can use a wireframe mode to check, wireframe here to check the mesh as a wireframe. And I will do the same with the rendering now. I don't know if you can notice, but the rendering mesh is made of quads, not triangles. So you see a different mesh for the collision detection and for the rendering, and for the mechanics. The mechanics, we just saw before that the mechanics is run on those hexa on this grid. So we have 3 different meshes for the 3 different representations. So this view panel will be useful to actually navigate from one representation to another. Okay. And the second widget, graph, is displaying the simulation graph. So here, for convenience, actually, I set some utility codes in a node called required plugin, but this one does nothing. Okay, it's just loading the dynamic libraries. But what we see apart from this required plugin, I'll get back to the regular view here. Visual, back up and in black on the bright side. Okay, and there we are. How many objects do we have in the simulation? 2, the snake, and the caduceus. Therefore, we have 2 child nodes, snake and base, that should be called actually caduceus, but that's the 2 objects. One will be static and rigid, that does not move and does not deform, it's the caduceus. This one does not deform, while the snake will bounce and deform around the caduceus. Okay? Let me see here. So the idea for us will be to start from an empty scene, add components, adding physics, adding solvers, integration scheme, linear solvers, rendering, adding some mappings, a collision model. So like a rendering model here, a collision model here, and then all that from XML, we're then going to move towards a Python script and do even more than what we did in XML with Python, okay? From here and from now on, so that's for the download materials if you would like to download them, if you did not, but that's where they are. And what I'd like us to achieve is this simulation having two objects in the scene, one rigid, one deformable, one which is actually, we will see that it's only, can you see, oh, you, sorry, you're not seeing your scene, sorry, stop sharing up. Window, content screen, yeah. Sorry, I was showing that here. So that's the plan of what we're gonna do, starting from an empty scene, adding physics on it, adding solvers, adding a rendering, a collision detection, representation, mappings, and moving everything towards Python. And the link I was referring to before is the link towards the scene file that you already downloaded, the example that we're going to run together. And what I'd like us to achieve is to run such a simulation with a deformable object, the lever in red. The lever will have a model for mechanics, obviously, that's the main one, but we will add a rendering, a collision model. It will be three-dimensional, deformable, while we will add a rigid particle, so like a rigid node, which therefore cannot deform, and that will collide with apparently a sphere collision primitive, collide against this deformable object. Okay? With that, obviously, we, as you already understood it and said it, we are not digging into all the different parts of SOFA very deep in the theoretical background, but with that, we'll cover a typical and already first scene of SOFA involving all the different aspects of the simulation that you will face for any other simulation using SOFA. Okay. So let's start with this basic scene. So I opened it myself in a file editor. It's here. What can you tell me about this simulation file here? What do you see? How does it start with? You know, it starts with a root node.
Your main root.
Yeah, exactly, which is starting the description of what is in the simulation. What can you see on this line of the root node? What do we define in addition to just the fact that we start to define the simulation?
So you have here the time pitch for the calculation.
Yeah, the time step exactly here. And as you can notice, we can as well, indeed, Ronak, we can as well define the gravity, which is a bit weird. I mean, it makes sense in the design of SOFA. But if you define a gravity here, always keep in mind this gravity, it's a gravitational acceleration. It will affect every object of your scene which has a mass. No gravitational force is rho, the mass density, times g, the gravitational acceleration. Here, what you define is g. If g is non-zero, therefore, as soon as you have a mass, a force will be applied on your object. So it's a generic definition for everything in the scene that there is possibly or not a gravity. Here, the gravity is 0.
Later
we open, yeah.
Yes, excuse me. Later on simulation, could you have several objects with some with mass and the other one without mass?
Yeah. But without mass, meaning that it's either a static resolution of what you want to do, or an object without a mass would be like a non-simulated object, something completely static that does not move, and you just want maybe to use as a collision detection object. Something, yeah, it's feasible. So what else do you see? There is actually one thing that I already mentioned before. So we are opening the node, we are closing the node. There is here a child node, but as you can notice here in the scene file, it's empty, completely empty. And we have two other objects. This one, actually, you can forget about it. It's just a manager, a loop for rendering. It's the rendering loop for displaying something in the graphical user interface of SOFA. But if I remove it, you will see, I will run the simulation, file, open, scene number 0, and you see it opens very well. And the visual manager loop is by default created because it's needed, and SOFA will create it itself. So no need to create it, just so that you know this visual manager loop is just in charge of rendering loop. But you remember we said root node, then we describe what is in the simulation, one child node for each object, and on top of the simulation, right after the root node, we must define an animation loop. The animation loop is the component, again, which is in charge of defining what happens within one time step. When I click on the step button, there will be things to be computed. The default animation loop is in charge of defining what happens here. If I'm going to remove and save again my file here, I'm going to file reload, or I can click on reload here. It's still working, still with the default animation loop. But here I have a very, very small, it's hard to see here, warning. If I double click on the root node, a window is opening, and you see there is a warning panel here, and I can see here message here. If you are using also the terminal as I'm using, you can even see the warning in the terminal here. So you have the warning in the terminal, a small widget in the graph here, and a message in the root node here. What does it say? It's saying actually, an animation loop is required, but none has been found. Add an animation loop in the root node to fix this warning. But just so that you know, we created one by default, which is the default animation loop. I really encourage you to always define an animation loop because it's actually important to know which one you're using. So here, I would rather keep the default animation loop. And if I reload, you see, there is no warning anymore. If I open here, I do not have a warning in the root node. As you might have noticed, when I'm double clicking on something, a node or a component, something opens. It's actually, we open the object, the component, the node, and what do we see? You remember how do we call those stuff here? The properties of components and nodes in the scene graph. How do we name them?
Data.
Data, exactly. So all those are the data. What we see here are all the data, all the parameters. Here, that's all the parameters of the root node. What do we see? The gravity. Again, that's what we defined. So we see the gravity, we see the time step that we defined, and we see as well the time. The root node is holding the information of what time is it in the simulation. So when you want to check what are the data, you can always double click on an object and check the data of this object. For instance, the node my object here, we'll check. We can check here. I defined something that is a bit hidden here. It's just a very specific case. The B box here is just used because I'm just adding that because the scene is empty. So in your case, as soon as you will load a mesh and so on, you won't use it. Why? Because the rendering of SOFA needs to know what's the size of objects to then create the rendering. And here it can't find anything. So to avoid guessing what's the size of something, I'm just giving it a box size saying, okay, if you want to make some rendering stuff later on, use that. -1, -1, -1 is the coordinate of the first corner, and the opposite corner of the box is 1, 1, 1. That's what I said. What I'm setting here. It's a detail because you'll see as soon as we have a mesh, this will be useless.
I have a question, Hugo.
Yeah.
Is it always in the time, or we could have a simulation in displacement, for example?
No, the time is actually what we are doing is two discretization, right? One in time, one in space. But what we will compute is an animation, a simulation. So we need to predetermine what's the amount of time we will go forward at each time so that we simulate a dynamic process.
Okay.
And at each time step, we'll have an update of all the position and displacement field of our objects. So we can access this information at each time step. Okay. So yeah, forgot to, as for instance, if I take still the scene number 0 base here, you see I gave a name. The name is one of the data, right? It's a parameter. It's one of the features of the node, but each object in the simulation, you can give it a name. For instance, the animation loop, I can also give it a name. You can call it very fancily animation loop here. I will save and open in Sofa, do reload. Did I 0 base? Am I doing something wrong? No, that's good. Sorry. Yeah, you see the node here of my default animation loop is well animation loop. But if you want really to make sure, and also our sheet save, I will reload, and you see that's the name of my object. So why giving a name to an object? Actually, because it will help us to find an object later on or to connect to an object later on if it has a proper name. So never hesitate neither to give proper names to your components that you're adding in the simulation so that you will always have here the name of the class, the C++ class, which is behind, but it can be pretty useful if you have some, for instance, several mesh loaders loading different meshes. Please use different names for the loaders to well identify which one is which one. All right, we'll move to the scene number 1 now. The scene number 1 takes the previous one. As you can notice, we still have the default animation loop. In the slide, I just hide it to make the slide a bit lighter, but we have the animation loop, the same root node, animation loop, and I'm creating now a node that I name particle. It's closed here, but I'm adding an object. Can you, anyone, Carolina, Guillaume, Ronak, Noel, feel free to re-explain me what is the role of the mechanical object? You remember? I said it's a passive component in Sofa, which has one role. It computes nothing, and it stores, it saves at each time step what you were interested in, Guillaume, the degrees of freedom, namely the position, therefore the displacement, and the velocities of each node. Okay? Yeah. Then, what can you guess from what I wrote here for the mechanical object? Do you have an idea what it means here? I divide 4 data. One which is called template, one which is called name, one which is called position, and one called show object.
So I think the objects apply, so the template apply a given behavior for this mechanical object, which is called rigid 3D. So
Yeah.
the name
Yeah. So the name is clear. Yeah.
And
What's
position is probably the initial position of the object at the start of the simulation.
Exactly. Exactly. So we are here. The most important thing, really the most important thing when you see a simulation file that you want to read, you see that there is a child node. So you guess it's going to be an object. You take a look at the child node here, particle. The thing you need to check first in a node is if there is a mechanical object, its template. Its template will actually define the nature of the degrees of freedom. It means if you are looking at a 3D object that deforms, we will use something called v23.06. We will use it later. If it's something which is moving but only on 1D, for instance, it could be a temperature, could simulate also temperatures, it will be vec1D. But for a deformable object, therefore, if it's deformable, it will be vec3D. And here we see rigid 3D. It means it's a rigid body in 3 dimensions. Why? Do you have an idea? The difference between vec3D and rigid 3D. In vec3D, the unknown would be X, Y, and Z. Yeah, Ronak? Yeah, go ahead.
It's a position and direction information.
Exactly, yeah, the orientation, correct. Yeah. And that's what we see here. We have 3 values which are X, Y, and Z. And we have 4 other ones which are a so-called quaternion. What is a quaternion? It's nothing else than an orientation, indeed. And let me show you an example. Here, it's a website that I like to go to, it's Quaternions Online. And you see, quaternions, it can be related to Euler angles, right? So basically, X, Y, and Z or Euler angles can be translated as W, X, Y, Z quaternions. It's an orientation, nothing else than an orientation. So that's what we defined here. What we are defining in the template is what is the nature, what's the size of the degrees of freedom at each node. Each node will have a number of unknown, basically, that we need to find at each time step. If we are using vec3D, it means what we need to find at each time step for each node is the position and velocity in X, Y, and Z, basically, where is the point in space. But if we model an object which has a mechanical object using a template, a rigid 3D, it means we will need to find at each time step a position, X, Y, Z, X, Y, and Z, and an orientation. That's what I wrote here in the file. In the file that we are actually loading here, it's just a comment saying that with rigid degrees of freedom, we have X, Y, Z, the position, and the quaternions here. That's for the position. And just so that you know, that's for the position. But if we take the derivative in time, so the velocity, we'll use the velocity in X, the velocity in Y, the velocity in Z. But if we take a look in SOFA, so I need to open file, I open the file number 1. So I open the file, the child node particle, and I double click on the mechanical object. I will have access to the state vectors, so my degrees of freedom. That's the one I manually define. But as you can notice from here, we have a vector for velocities, which is 3 plus 3, not 3 plus 4. Why? Because actually the velocity is expressed using angular velocities around X, Y, and Z. It's Euler velocity angles, angle velocity. Okay. So that's the reason why I'm actually saying, the reason why I'm actually saying it's very important to check the template. It's because the dimension of your vector of position will not be the same. If you have 10 nodes, and you are using a template of vec3, you have 10 times 3 xyz, 10 times 3 unknown, xyz of point 1 of node 1, xyz of node 2, xyz of node 3, and so on and so on and so forth. While if you are using rigid, here you'll have again position and orientation, which are computed for a rigid body. So if we load this file here in SOFA, that's what we have. So I'm going to reload it. We have the root node still. If I double click, still the gravity, time step, time here. By default animation loop, and a particle child node named particle, which has a mechanical object, okay, just like we defined above here. And if I double click on it, I can check here the template. The template, you can find it here in the widget called info. Info template is rigid 3D. Okay. So we do have indeed a template which is rigid. That's a way to check what's the template. And as you can notice here, the state contains the position, so the degrees of freedom of my problem, and the velocity, the derivative, the first derivative in time of my degrees of freedom. Okay. What you might have noticed here, something that could be confusing for you here, is that I'm starting to add something called required plugin. Why? Because it's written here as a comment. We are using as a component, we are using the mechanical object. The mechanical object belongs to SOFA, and it belongs to SOFA. It's saved, it's located into some kind of module of SOFA. Therefore, a dynamic library, which is compiled when we compile SOFA. And the dynamic library is called sofa.component.stateContainer. You remember, it's exactly the same place where we save the files. So the name of the libraries are mirroring the architecture of SOFA. And because this component mechanical object is located here, what I like is to add in my scene, okay, here I'm using this part of SOFA. That's all what I'm saying here. But actually, this is just to make a very clean scene because it works as well without writing that. Okay. If I don't write this, I will reload the simulation. And if I check here in my terminal, I have some warnings just for developers, for a warning which is appearing only in the command window, which is telling you what? Make that a bit smaller, okay. Which is telling you what? Sorry. Which is telling you exactly what I wrote here. You're using a dynamic library. You're using a dynamic library that you did not specify. It's this one. If you want to remove this warning, just add this line into your XML script. Okay, that's it. Otherwise, it works the same because it's a library which is compiled with SOFA. If you are using some random plugin of yours that SOFA is not aware of, you will need to spend here. It will be required to add this line, required plugin, the name of your plugin. Okay. All right. Let me know if there is any question so far. Do not let me carry on whether there is any things to be clarified.
Show object is one. It means that it's true again. I'm
sorry. What did you say?
The show object. The last parameter.
Yeah. Thanks. Show object is actually just an option for forcing the rendering of this frame. It's a rigid frame. You agree with that? We define one point here manually. We are defining the fact that we have one rigid frame with its position 0, 0, 0, and its orientation using a quaternion 0001. And using the show object, what we do is that if I hide the axis here, because I was pushing the A key of the keyboard, but I have this small particle here. This is due to the fact that I activated this option here. For instance, let's go back to the mechanical object. And let me, in the visualization widget, deactivate this show object, and then click update. The frame disappears. It's just it's some kind of a debug tool that we like to use to check where are those rigid frames. Okay. And here, no need to play with this view panel. It automatically render it. Thank you for the question.
Thanks.
Let's go further. We have a rigid particle. So what we want is little by little to make it move. At least I'd like to make it move. So let's add it. Let's add to this particle a mass. And here you see the total mass of this particle is 1. And I'd like to make it move. I don't have any gravity for now. So what I'm going to do is, without playing with a gravity field, I'm going to apply a constant external force to this particle. This force is actually homogeneous to in the dimension is homogeneous to a velocity. Therefore, you remember I said before that in SOFA, when we have a rigid object, the velocity is velocity in x and y and z, and the angular velocity in x, y, and z. So we have 6 values. So therefore, we have a force here, 1, 2, 3, 1, 2, 3. We have a translational force in x, in y, in z, and a torque that we apply in x, in y, around x, around y, around z. Okay? Can you open this file number 2? Sorry, the file number 2 here, file open number 2 here, to mass and force. Click on the animate button and let me know what you see. And can you maybe find an explanation to it? Carolina, are you able to, have you already SOFA open and able to run it? You're muted, but let me know if you, what happens?
Nothing happens.
Yeah, correct, yeah. Nothing happens. So I'm going to do that with you. So yeah, I click on animate. Nothing happens. It's not completely true. There is one thing that happens. Look here. Time passes by. Okay. Why? I told you earlier. What did I tell you about the animation loop? It defines the steps to be computed within one time step, and then goes to the next. If there is some collision detection to be computed, it will call a collision pipeline, but here, for the moment, we don't have any. So, skipped. And actually, then, to compute the mechanics, an animation loop is looking for an integration scheme. Someone which is able to build the system in order to find the velocity and the position at the next time step. We have none. We have no integration schemes. Therefore, even if you could put as many things as you would like, as like 10 masses or whatever, or increase the mass by hundreds, 10,000, whatever, it would not change anything, because the animation loop, which is, just as a reminder, here, the animation loop, which is here, there, is blind, is considering that the scene is completely empty. It does not see any collision pipeline. It does not see any integration scheme for the animation loop. It's giving orders. Nobody is able to answer. Okay, next time step, and that's it. So basically, we have empty loops running on the animation loop level. So that's why time is passing by, but in fact, nothing is computed within each time step. So what is missing is definitely what I like to call solvers, but it's two things. Yeah, there is really two different things. The integration scheme, defining how to build AX equal B system in order to find the new position and velocities at the next time step. Here, it's the one that is called Euler implicit solver. Does that ring a bell to someone? Euler implicit? Does anyone has already heard that somehow? Euler implicit, Euler explicit? No? All right. And the other one, which is the guy in charge of solving the linear system, the linear solver. Now, if we had that here, so I will here just open the scene number 3. We have the animation loop. And now the animation loop will be able to find an integration scheme. Therefore, you remember, it has this one has 2 steps: collision detection, computation of the mechanics. And for the second step, computation of the mechanics, it's seeking, looking for an integration scheme. Here, there is one. It will be automatically found at the initialization of the simulation, and the connection is automatic. So now, if I load the scene number 3, and you can do that with me, scene number 3, I still have my rigid particle, which is here in 0, 0, 0, and get ready. In which direction is gonna be? It's gonna move. Is my particle gonna move? You remember the force? It's a translational force along
X direction.
Correct. Yeah, along X. I click on animate. Did you see it? I'm gonna reload it and do that again. See, I'm running and stopping. Sorry. Reloading. Particle is here. I'll do that step by step. Now, step by step, you see. I'm keeping the step button pressed, so it's doing a step-by-step slow process. My particle is indeed moving towards the x-axis. Again, the axis here, I'm highlighting them with the A key of the keyboard. All right, so now we got something moving. We've got a rigid particle that we define the initial position, as you said, Guillaume, here, x, y, z, the initial orientation here. We most importantly define what's the nature of the degrees of freedom we are talking about. We assign to this particle a mass, an external force, and we give the appropriate numerical tools to solve the problem. As you might have noticed, I have additional required plugins here because I'm using more and more components. Therefore, they are located in different libraries. But again, this does not matter. Okay, all that belongs to SOFA. So if you forget to specify one required plugin, all that you're gonna have is a small warning in the command window, nothing else. Okay. Is there a question about that here, about that simulation here? I can, like that, it's gonna be lighter. No? No question so far? Just in case you get back to the files and to the presentation maybe later on, you might notice that here I added something just to keep everything very transparent to you. This is just a very simple option to avoid, as you can notice, it's set to false, so it's deactivated. We deactivate the computation of the bounding box. Again, the rendering bounding box. Why? Because since the particle is moving to the infinity, this box would grow forever and ever. And if I let the simulation run, I would have some rendering discrepancy stuff that would appear on the screen just because the particle goes to the infinity. Okay, so that's the reason why. I just want to keep my focus the same as the beginning. So I'm losing I'm losing the particle from side, but it doesn't matter. Okay, just and anyhow, else the same particle as before. So the child node. Integration scheme, linear solver, the mechanical object which is storing the degrees of freedom. So we need to specify what is the nature of the degrees of freedom. I insist on that. It's really key to understand. When I see that, I see a rigid object immediately. When I'm reading just in one line, like in one shot of the file, that's my way of reading things. I can immediately consider all this whole node as a rigid object. It has a rigid template. Then I can check here its degrees of freedom, so its position, and I immediately know that we don't have only a position, but we also have an orientation with it. What I also immediately know is that there is no need to define a deformable material law somehow, right? What I called earlier a constitutive mechanical law. Here it's a rigid object. There is no deformation. So no elasticity, nothing, no. A rigid object, you have a mass and external forces. That's it. If you apply a force, it moves. It does not deform. It moves straight away. That's the principle of a rigid object. So that's why templates can really help you reading and understanding the nature of the object that you have. And on top of that, the nature of the degrees of freedom which are used for this object. One last, yeah, go ahead.
And what is B-box? Is like to compute the intersection between the objects?
Yeah, no, here it's the same than this bounding box, B-box, bounding box. Those two here are actually a rendering bounding box. Okay, so basically what we say here in those two lines, the line number 12 and 14, is that the bounding box that we will use for the rendering, it's something which is just used to render things and so on. If something is outside this box, it's not rendered. That's what it says. The box is between -1, -1, -1, and +1, +1, +1. And by specifying that, what I do, what I'm explaining here, what I'm expliciting is that we will never recompute it. While if you don't specify that, SOFA automatically, when something moves, rearrange the size of the rendering box. Okay, but it's just for rendering, so you can really forget about those compute bounding box, B box in the node or in the root node. It's just a detail. Okay, and it's actually just due to the fact we are using just for the moment one particle, one single node, one single frame.
Okay. Frame. It's like the viewpoint. That if we change the viewpoint, I think it should be changed. I don't know.
Yeah, it might, but the size of the box will remain the same.
Okay.
For the moment, because we made it static here. I thought you were going to ask something else. I thought you were going to ask exactly what are those stuff after the CG linear solver. I'm going to ask you, what are those? Those are property of the class of the object CG linear solver. CG stands for conjugate gradient linear solver.
It's the number of iterations and.
So that's the property. So again, in SOFA, we call that the data, right? It's the data which are specific to the CG linear solver. And what are, so the CG, the conjugate gradient is a method to solve a linear matrix system, but to solve it iteratively.
Yes.
It means it's a way to find an approximated solution, and we are here, we are giving us some so-called stop condition or breaking condition. It means if the solution we find requires more than 200 iterations, we stop. If the solution we find is like the convergence falls below this 10 to the power of -9, then we will stop. Okay, here, these are convergence and accuracy criteria. Here, it's an iteration criteria. Basically, you try to bound, you give bounds boundaries to your iteration so that it stops sometime, to know when to stop. Okay, that's why I added that here. If you forget to put them, this component would complain. It would say, I'm sorry, but those I need, otherwise I can't know when to stop. I have some default values, I'm going to use them, but please make sure that those default values are the good ones. Okay? So you would have some complaints.
Is it something you play really often with these parameters?
No, because actually those parameters. So iteration will definitely depends on the number of iterations. Therefore, depends on the convergence, how good you converge to a solution. And there, actually, what you need to make sure is that you converge. So you need to first make sure that changing this value does not affect the quality of the result. And those two here are actually depending on the maximal error that you would accept. If you can tell me my maximum error is like a 1 millimeter and you are using meters, then it would be 10 to the power of -3. Those values, usually tolerance and threshold, we put that equal to the square of this error. Therefore, 10 to the power of -6 squared, 10 to the power of -3 squared. Therefore, it's 10 to the power of -6. Okay, just so that you know how to set them up. That's the way. When you have like one object, when you know the error that you're ready to do, no, you don't really use them. Otherwise, there is another class of linear solvers called direct methods, direct linear solvers. For those, they will actually exactly solve the problem, find the exact solution. And here, you don't need to set any parameters. It's another family of method, which is, solving the AX equal B problem. But instead of finding some guesses of X, guesses of the solution, and converging towards the solution, those other direct methods, they are finding what? They are actually, they are factorizing the A matrix. So finding a way to reorganize the A matrix so that you can easily inverse A and compute A minus 1 times B. A minus 1 times B, that's X. Okay, that's two families of linear solvers. Here we are using an iterative one, therefore I need to specify some breaking condition for the iteration.
Sorry,
Okay.
I have another question.
Yeah, go ahead.
Can A matrix and B vector be, because here I think it is constant, right? Because B is a constant vector, but if we want to be dependent, for example, on some parameter.
This will be defined. So usually what you're asking is, can I have some forces which are not constant? And therefore, if I have forces that are not constant, B will change, maybe not constant in time, or maybe the forces depend on the position of my object. Typically, a mechanical model, a mechanical constitutive law, when it deforms, it's something that will depend on the state. So it will not be constant, or possibly not constant. And therefore, this is implemented in those so-called force fields. But the API of SOFA makes it automatic to recompute B and recompute A all the time at each time step. Okay.
Okay.
We will cover the way we actually compute A and B shortly. It will be really at the end of the session, in the math to the code session. Any other question, Carolina or Guillaume? If you have any other question, do not hesitate.
Well, yeah. I see there are many solvers in SOFA, really. So why, in this case, we're using CG linear solver?
Yeah, that's so. This is a complicated question. I mean, or at least the answer would be complicated. That's what I told you about, having some backgrounds on numerical analysis. this is, I would say, somehow the art of numerical analysis. It's to know when to use an implicit integration scheme. It's a family. It's one of the family of integration scheme. When to use an explicit one, or when to use a direct solvers. That's what I just said, to inverse the A matrix, or when to use an iterative solver. That's what we have here. So when to use a direct or iterative, it will be usually a question of performances. In some cases, direct solver will be more efficient. In some others, iterative ones would be more efficient. So it depends. And unfortunately, on all those topics of numerical analysis, the answer is it depends. It depends exactly really on the exact problem you're looking at and on the kind of optimization you want to do and so on and so forth. We try to detail a bit, you know, how the main ones are working in the documentation of SOFA. But yeah, what I can tell you as a basis is if you are looking at a static problem, we have a static solver. So here it means no dynamic and no mass. If you are interested in dynamic processes, usually when we talk about dynamic simulation, we like to use some schemes like the Euler implicit scheme, because this one is very convenient. Is a so-called dissipative schemes. It means that is dissipating, losing some energy among time, which is actually good because we tend in simulation to sometimes, I would say, virtually to introduce some additional energy in the system, and this is a way to keep the simulation stable all the time, to use a Euler implicit scheme. About direct or iterative solvers for the second line about CG linear solver, as I said, if you don't know, you can ask on the forum for explaining your specific case. But usually it depends on the size of your problem. Basically, how many degrees of freedom you have to solve. Therefore, how fine is your mesh? Finally, the more points you have, the bigger your system will be. The complexity of the problem. What is inside the A matrix? You know, how does the matrix look like? Is that a diagonal matrix? Is that a symmetric matrix, a positive symmetric definite matrix? Well, that's all that will define whether one or the other would be more suitable. Okay. But again, for if I can give you some insight for like the most commonly used ones for linear solvers would be for direct solvers, one which is called sparse LDL, which is decomposing the A matrix into a lower part L and a diagonal part LDL, and trying to inverse A. And the CG, conjugate gradient linear solver, is the one for iterative processes which is used. But again, iterative meaning that you will have only an approximated solution.
Okay, thank you.
It's already a bit too much, what I just said, but just to explain, it gives also an idea that this topic of numerical analysis takes a bit of time to be explained and to dig into it. Okay. And we have some specific slides and specific presentations for that. If you'd like, again, to take some time later on in some other sessions to dig into it. All right. So we had a root node empty. We saw that we need a default animation loop, which defines what are the steps to be computed. By default, if we forget one, there is the default animation loop. But again, we should better is to define really ourselves the animation loop. Then we created a node, a child node particle, in which we added the mechanical object. It defines what's the nature of the degrees of freedom, rigid or deformable, and according to that, it will create a vector of state of degrees of freedom containing the position and possibly, if it's rigid, the orientation of our object. We added the physics and we added the integration scheme and the linear solver. Now it's moving. We have a mass, a force. as you might know it under the Newton's law, the mass times the acceleration is equal to the force. We have a mass, we have a force, so we have an acceleration. The object is moving. Can you tell me in that case, therefore, looking at the total mass value and the constant and the constant force field total force, what is, and I'm going to open SOFA here, I'm at the time equal to, what's the velocity inside my mechanical object? Do not open it. Can you guess it? I mean, can you compute it? Because it can be just manually computed. We have the mass times the acceleration is equal to the force, right? So if I write it here, mass times the acceleration is equal to the force. My mass is equal to 1. It's written here. My force is equal to 1 in x, 0 elsewhere. So it means that my acceleration in x, if I take the acceleration in x, is equal to what?
1.
F, exactly, to 1. F, 1 divided by m, 1, therefore 1. It means that the velocity, if I in x, is equal to the integral over time of 1. It means a constant. We have a constant velocity. We have a linear velocity, sorry, against the time. We have 1 time t. We have a constant acceleration, which is equal to 1. Therefore, we have a constant increase of the velocity. Therefore, we have v of x of t is equal to t. T is 1, time is 1, time is equal to 2, time is equal to 2. Let's check the velocity. It's equal to 2. If I increase the time, you see, time is equal to velocity. Velocity in the x direction is equal to the time. Okay. All right. From now on, we worked with one single rigid particle, but the idea is that up to a point, especially when we look at 3D deformable object, for the moment we are rigid, but up to a point we will look at a deformable object. I guess you won't be interested in specifying the position of each node manually. What we would like to do is to load a mesh. So this will be a dummy example here. We will, instead of running the simulation on one rigid particle, we will create several particles, but not ourselves. We'd like to load them from a file. I mean, we're lazy, and that's a good property. So we still have the root node as before, its name, the time step dt, gravity is equal to 0. But just after, we have the default animation loop that is hidden here on the slide. But if we take a look in the file here, file number 4, we have the default animation loop, which is here. But we are adding one line, which is a mesh loader. In fact, we are loading an MSH format here, so it's a mesh gmesh because it's coming from the gmesh software. Mesh gmesh loader. I give a name to this loader, to this component in SOFA. I call it mesh loader course, and I give the path. Can be relative or absolute. I give the path to my file, lever.msh. So what does the mesh loader, mesh gmesh loader in that case? All the loaders are working the same. They are loading the file, loading all the topology information from this file at the initialization of the simulation, and then nothing. Then, during the whole simulation, it will be passive. It's a component that loads the topology information, makes it available for anyone to use it later on. Actually, it has some data itself, some vectors and so on, containing the number of points, the position of each node, and so on and so forth. If there is triangles, what are the nodes connecting this triangle, and so on. Same for edges, same for hexas, if there is hexa, if there is tetra, and so on. But it's just offering those data to anyone in the simulation that wants to access it. But its job is done. Once the simulation is initialized, the mesh is loaded, and that's it. So we load it, and I like to put it up in the scene so that anyone in the simulation later on can access this mesh loader, so-called mesh loader course, easily. In my node, now I call it lever, but it doesn't matter. I'm adding something which is called a set topology container. This guy is a container for the topology. As you can notice, it is connecting to the mesh loader. Can you see that? We are using here a writing that tells that use as a source, SRC stands for source, use as a source of information everything that you find in the mesh loader course at ... meaning it's in the node above, mesh loader course. And then automatically, what does the container, the topology container, is that it will check in the mesh loader if it has some, in this case, you can notice it's a point set topology container. So we are only interested in nodes, in points. We don't care about edges, we don't care about triangles. It's the lowest hierarchy of topology, it's only the points. So we are keeping the number of point information and the list of those points and their location, their position in space. We are copying that at initialization from the loader to the topology. What can you notice from the mechanical object? Something disappeared. Can you notice what disappeared in the mechanical object? Let me show that again to you.
Well, I guess its name is mechanical loadable. And
Yeah.
as mentioned, it has the position and the location.
Exactly. Yeah. The whole data field position disappeared. Why? Because what happens when the simulation is initialized? The mesh loader loads the mesh information, the whole topology information. Just so that you know, this mesh lever.msh, it contains a lot of things. It contains nodes information, edges information, triangles information, and it contains even tetrahedra. It contains a full 3D mesh made of tetrahedra. But here, we are only using a point topology container. So the only thing we will copy from this mesh loader for the moment is only the point information, nothing else. We will copy the position of all those nodes, and something which is done implicitly by SOFA, a bit behind your back. I will look at the file here. Is that the mechanical object? You see the position field disappeared, but in fact, what is automatically done when a topology container is in the same node as the mechanical object is looking for a container. It finds the container named topo, or topology. You give the name, you give the name you want. Huh? It finds the topology, and what does it do? It does that. Position of my mechanical object for the initialization are equal to the position we just loaded in the topology. If node is given here, if I save that, you'll see it gives the very same result as the default scene, number 4. That's, we get these point clouds of rigid frames. Okay? So if I remove that, I will save that again. And look at that, I will reload. Reload. Nothing changed. No, it's done automatically. The mechanical object is directly linking itself to the container at the initialization to initialize its position data field. And same for the velocity, which are by default set to 0. Okay? In the file here, there is an example on how to apply a transformation. If your mesh is not suiting you because it's not in the right place or whatever, you have the possibility to apply some transformation to it. So that's an example of that, where you can use so-called engine. Engine, it's some kind of processors. They have input, output, and they do something in between. Here it's a transformation, translation, or rotation. And then what we can do then is to use this new translated stuff into our object here, for instance. I think this should work this way. Sorry. I'll do that slower, and it's better. Have you noticed? I don't know if you noticed, I'm going to remove what I just did here. Instead of using the new position in my mechanical object, the new position after translation, I will remove that, and I can comment again to remove the transformation. Look at my point cloud; it will go down closer to 0, 0, 0. Okay. So if you want, just so that you know, you can apply transformations to a mesh that you loaded, and then the topology is the same. The topology is the same. Just you can provide a new configuration, so new position, possibly an orientation to your mechanical object. Here, I don't know if you noticed, but what happened is that, so I'm going to do that again, here. When I had this transformation engine, it's taking as input the position here that we loaded. We apply a translation along y of 2. This name is called, the component is called transformers, a transformer. I'm connecting to this guy in my data field position, and I'm recovering the output position after translation. All right. Again, if I forget about this translation, if I don't even put a position data field, it works because my container has already an information of position of my nodes here, of my rigid particles, and it's contained here and copied directly in the mechanical object at the init. All right, a small question. We have still a mass of 1. We have still a constant force. Total force is equal to 1. What's going to be the velocity at times equal to? Don't. Yeah, why?
Because it's equal to t.
Exactly, yeah. The mass of each small rigid particle has been divided by the number of nodes, because it's a total mass. The mass is spread over the number of nodes with this uniform mass. And the constant force field, it works the same. Basically, it's a nodal mass and a nodal force. And here, the nodal force is 1 over the number of nodes, and the nodal mass is the same, 1 over the number of nodes. So we have the same value on the left, the same value on the right. Again, the acceleration for the mass and force. So the acceleration is still 1. So the velocity is indeed still equal to t, 1 times t. So we have indeed at time 2 is equal to 2, velocity is equal to 2. All right. So my question was, is that moving faster, slower, or same acceleration? The answer is same acceleration. careful here. If I run the animation, you might, from the rendering, say you might say, oh, it looks like it goes a bit slower. Don't get tricked by the level of zoom, right? We are just a bit far from the object, a bit more away from the object. And therefore, the object looks a bit slower. But in fact, acceleration is the very same as before. All right, just checking the time. Okay, it's already almost like 1 here. It's some kind of lunch time, so it's a quarter to 1. Not for you, Nurul and Carolina, but I suggest we do a break here. We can do like a 1 hour break if it's fine. Not too long. I mean, sometimes when we are on site, we do a bit more, like 1 hour and 30 minutes, or even sometimes more. But I'll suggest to keep that to 1 hour. Is that fine for everyone?
Yeah, it's okay for me.
Cool. So let's say that at 1:35 we restart. We will restart from here, and we will finally, from a rigid case, from those rigid particles, change the scene, make the scene evolve, and move towards a deformable object. Okay? Then we will move to Python, and then we will take again one last time the whole tutorial and make the relationship between what we saw, the theoretical background, the equation basically, the code, and the simulation we got so far. Okay? So have a good break. I'm gonna mute myself, and I think I'll keep the recording running just so that I don't forget about it. And we'll, yeah, see you now a bit less than an hour, but have a good lunch, or maybe a good breakfast for you, Carolina. I don't know. See you there. And if you have some questions for some of you guys, I can stay connected a bit. Yeah, for some questions.
Okay.
See you there.
See you later.
So we stopped here just before the break, where we discovered how to build really step by step this simulation up to the point where we had one rigid frame that was pushed under a constant force with a mass and a constant force in the x direction. And finally, what we added just at the end was to have the possibility to automatically load a set of positions from a mesh, actually, to use and exploit data that were contained into a mesh somewhere on your machine, or that you would have generated prior to your simulation. So we will move from that to a deformable case. Basically, we had so far rigid frames, and we will have now a deformable object. Is there, or were there, some question that you had, or from the previous part, or is that good? And let's carry on.
Just a practical question. When you switch to the code view, is it through the web page?
No, it's you mean that here, or yeah, here it's a text editor that I'm using, which is called Sublime, and Sublime is like a text editor that allows you to open any kind of XML, Python, or whatever. So you open an editor, and I'm just opening the scene files that I sent you. They're on the left here. That's okay. the entire repository, the entire folder that I sent you as a zip, and I'm opening them one by one.
Okay.
All right. So, can you remember in the previous part of the training what defined in the simulation the kind of object, the kind of degrees of freedom we were working with? What is defining that in the scene? It was among the first objects we added. and it had a data. Yeah, Ronak?
It was template.
Yeah, correct. The template of the mechanical object. The mechanical object is specifying the nature of the degrees of freedom that we are using for this object. Actually, this is one of the main and only stuff that will change if we go from a rigid to a deformable case. Look here at the mechanical object. Mechanical object now has a template, Vec3D, not anymore rigid 3D. It's a 3D object, but that will be possibly deformable, meaning that the degrees of freedom are not anymore a position and an orientation at each node, at each rigid frame, but instead of that, we only have nodes with X, Y, Z position, and that's it. These are the unknown at each node of the mesh. But to have something that will deform in 3D, we get back a bit to the point you raised before, Guillaume, about the kind of modeling. Is that a 1D model, a 2D model, or a 3D model? Let's take a generic, let's say, a random 3D object, 3D shape. Then we need to use a 3D finite element method approach where we will need a mesh in 3D with volumetric element that will allow us to compute the integral in space of the equation, basically, to solve the mechanical equilibrium equation in space in 3D. For that, we need a 3D support in space, so 3D elements. I told you earlier that the lever.msh does not only contain points, but it does also contain edges, triangle, and tetrahedra. And tetrahedra, those are elements in 3D, right? Those are like four faces elements in 3D with a volume connected through edges with faces, which are triangles, and so on and so forth. All this information, all this topological information is contained and loaded by the mesh loader. What we did earlier with a rigid frame, we will do the same. But instead of a point set topology container, if we want to work in 3D, knowing that we have tetrahedral elements, we will use a tetrahedron set topology container that will, in the same way, as you can notice here, I'll take my pointer again, but you see, we have src at mesh loader course as before, but since we are not anymore only interested in the point information, but the whole hierarchy of topology, tetra, triangle, edges, and points. All this will be stored. So first it's loaded by the mesh loader and then stored by this topology container. Therefore, as before, no need to specify manually in the mechanical object the initial position. They will be automatically initialized because the mechanical object will find a container and initialize the position of the object. And this guy, the geometry algorithm, and the two other guys here, they are somehow connected. Because the tetrahedron set geometry algorithm is a toolkit. It's not actually actively computing something, but it's a toolkit that will allow other codes like this one and this one, the tetrahedron FEM force field and the mesh matrix mass, those two components, they will need to do what? A space integration. To do a space integration, we'll need to have information like what's the volume of the tetra number 10, what's the area of the triangle number 8, and so on. This toolkit offers this. It's a toolkit that will compute geometrical information, like what's the volume of this tetra, what's the distance between those 2 points, and that kind of things. Okay? And it will be used by the physics when the physics, those codes actually, the tetrahedron FEM force field and mesh matrix mass are responsible for the space integration for the mesh matrix mass of a mass density. So when you give a mass density, the mesh matrix mass is able to integrate it in space to build a mass matrix. And the first one is implementing, can you guess what it's actually, I'm going to tell you, it's a a constitutive mechanical model. Can you guess what constitutive mechanical model it is? It means it's a model which defines how the object will deform. We sometimes also call that internal forces because it's basically the material itself. What kind of material is that? What kind of material law is that? What kind of constitutive law is that? In mechanics, we have, like several hyper-elastic models, like it's non-linear mechanical model. There's plenty of them. Just to say some names, like Mooney-Rivlin is one of them, Ogden is one of them. So it's the name of some non-linear models. But this one, does that recall something to you?
I would say elastic.
Exactly.
Elastic.
Exactly. It's linear elasticity. Linear elasticity, and this component has the possibility to do like in small or large displacement. It's actually two hypotheses that you can choose whether you have small or large displacement on your in your mechanics. But it's indeed a mechanical law which is known as the linear elasticity. And the name of this law, when we consider only small displacement, so something which does not deform too much, it's known as the Hooke's law. Also, that's the other name that you might have heard before. Hooke's law, or a linear, it's the specificity of linear elasticity for small deformation. This one, it's linear elasticity. Small or large deformation, we can change that in the code. Young modulus, do you remember what it does correspond to? What is the meaning of the Young modulus?
It's in megapascal.
So it's related to it's homogeneous to a pressure, yes. For the unit, but what does it mean? What is that for material? If we have a high Young modulus or a low Young modulus, what does that mean?
It will be more rigid or more flexible, I would say.
Yeah, stiffer or indeed more flexible. Yeah. And the Poisson ratio is like a compressibility ratio that will give how much it expands in one direction when you compress in the other direction. That's what it means. So for more details about that, about the material itself, you can either look at the doc or there is not much doc on this one, but I should write it sometime soon. And otherwise, I mean, it's pretty well documented. Hooke's law, linear elasticity, it's pretty common. So you see that we had before a rigid frame with a position and orientation, a mass. This rigid frame also had an external force, which is still here, right? The constant force field is still, I kept it for the moment, that was pushing the particle. But since it was a rigid object with the template rigid 3D in the mechanical object, it cannot deform, and any force applied creates a motion. Here we have and it was a nodal particle, right? It was just one point in space that was moving with the mass associated to it, but only one point in space, a particle, a rigid frame in space moving. Here, it's completely different. We have a 3D mesh. We are loading and using this 3D mesh as our domain of space integration. So that's on this domain, we will compute the mechanics. And on this domain, we will take into account a mass density integrated over the domain, a material law, here linear elasticity, which is integrated over the domain using the finite element method. And there is some nodal forces still with a constant force field, which are some kind of external force, right? It's an external force applied in that case on all the nodes with a total force of 1, 0, 0, meaning that we apply what kind of force? There is no trick here. What does that mean? Yeah. Onak, sorry, you're muted.
Sorry, what was the question?
So you see, so I said we have the material law here, the mass with the mass density, which is integrated over the domain, and the constant force field, which is applying some nodal, on the nodes, nodal forces.
Yeah.
1, 0, 0. What does that mean, this 1, 0, 0? We apply...
The force is in the x direction.
On all the nodes, we apply a force of 1 in x, 0 elsewhere. Why 1, 0, 0? Because now the degrees of freedom, the template, is vector D. So we don't have any notion of, rotation or of my rigid frame. We don't have a frame anymore. We have just a node, a point in space without orientation. So the force has itself only 3 degrees of freedom. X, Y, and Z, the translational force in X, Y, and Z. Okay. Here, usually, sometimes I got the question, do you have any question? Because here on what you look at, for instance, if you look at the line of the tetrahedron FEM for finite element method, force field, do you have a question about this guy, which is implementing the linear elasticity based on the finite element method on tetrahedra? Look at the data. Any question about the data? Especially the value, which is given. Related to your remark, Guillaume, earlier.
No.
What are...
We go to take in a mesh loader?
So here we are using the mesh loader already. So loading the mesh and using this, this 3D mesh as the support for, and this will represent now our object, and that's where the mass will be computed, the stiffness will be computed, and so on. Now there is something here about the unit. What I was curious is, since the beginning, we are talking about the time step, the time. What are the unit of that? What are the unit of the Young modulus? What are the unit of the mass density?
We suppose it's international units. So
what?
Poisson ratio, it's no.
It has no unit. It's dimensionless.
Yes. Okay. Young modulus should be megapascal.
So here, my other question, if you say that, is why megapascal? Why? What tells you that megapascal would be the pressure unit in that case? The question of units is that it has, and you said it indirectly, Guillaume. You said, but we are using the international system unit. I mean, no, nowhere it's written that we should or we must, and there is no check that your mesh is indeed in meters or whatever.
Yes.
The important point is that the user, you have to pay attention that the mesh you give, the value that you set for the Young modulus and so on are using the same units. SOFA doesn't care about SOFA doesn't care about units. Basically, it takes values and solve those values in a matrix and stuff like that. But we really need to be careful about the coherency of what we give to SOFA. If we provide a mesh which is in millimeters and that we use for some other values meters, for instance, gravitational acceleration is an acceleration. So acceleration, it's a distance over time squared. So it means that we have the length unit divided by the time unit minus to the power of -2. We really should think like that. What is my length unit? What is my time unit? What is my mass unit? As soon as you specify that, I mean, easy. If you are just using always, all the time, international system units, no problem. It will be by default, since you are using only this, it will be coherent. But megapascal is no international system unit. Pascal is. megapascal is actually, for instance, if the Young modulus is 1 megapascal of your material and your mesh is using millimeters, then your Young modulus should be expressed in megapascal, so 1. If you go back to meters in your mesh, then it goes back to 10 to the power of 6 Pascal. Yeah. So you see, depending on what you specify on one of the units, make sure that all the others, depending on this unit, again, length unit, mass unit, time unit, make them coherent, and then you're free to do whatever you want. What I usually errors come from the mesh, which is either in units that people do not know, like sometimes even no units, just come from a scanner, which is not even a 3D scan. It's meshed, and then you have possibly no units. It's something that has been scaled on the MRI, on the scan, or whatever. So you need to make sure of the size and the dimension of your mesh. Or sometimes people are just using either millimeters, or some guys, there is still people using inches on Earth. So some translation between units. But again, coherency, and with that you're saved and you're safe. Okay. So far, we achieved a full mechanical model. We have a root node, a loader, loading so we have the root node, we have the default, an animation loop in charge of defining what happens within one time step. Here, a mesh loader, so that we load the mesh at the initialization, and one object in which we have everything for this object to move, and in that case, even deform, because it's a deformable object. An integration scheme, a linear solver, the topology which is contained in the topology container, mechanical object, storing the degrees of freedom, and the physics with the mechanical constitutive law, linear elasticity, the mass with the mass density, and an external force applied to my object. This is it. Okay. Okay, something went through my mind and left straight away. I'll get to that later on. So let's add another representation. We said earlier that we could actually decouple all those representations. Let's add, for instance, first rendering model. So far, the rendering model will use the very same mesh. Okay, as you can notice, it's connected to mesh loader cores. So the one above loaded by the mesh gmesh loader, which is here. So we should visualize the same thing than what we actually use for the physics. Let's open the scene number. So I forgot to run the scene with the constant force and linear elasticity. It was this one. All right. We had, sorry, to get back to this case here, to the slide just before, with a full deformation model we achieved. We are loading a mesh. Sorry. We are loading a mesh, a 3D mesh, and we are using it for our simulation. You remember there is, so it's a linear elastic model with the mass and a constant force pushing it along X. And I will reload the scene. And I will visualize here. So I'm activating the force field in the view. It's activated. And in constant force field, I will double click here. Visualization, and I will increase the show arrow size here up to 100. And as you can notice, that's my nodal force, the constant force field, applying a constant nodal force on each of the nodes of my mesh. So these actually, the green arrows are actually the reason why it's sliding along X, right? But the big difference compared to before is that now we have a constitutive model. It comes from this equation from continuum mechanics. What does that mean, continuum? Continuum It means that it's a continuous object. It means that even if I discretize it, what happens on one node will affect the others. It's one object. So if I press the Shift key of the keyboard and then the left mouse button, it creates a spring between my mouse and my lever. And there you can really see that it's a deformable object, right? It really deforms due to the spring, which is now attached at one of the nodes. If I was doing that with the previous case, what would happen in that case? Those were single particles, independent from another. If I grab one, they are completely independent. These are just some rigid frames not connected one to another. And therefore, what happens to one does not affect the other. The other, in the case where we use this 3D model, what means 3D is that we have this space integration. And therefore, what happens somewhere will affect the entire domain, the entire continuous object. Sorry, I should have explained that earlier. So the idea was now to add another representation, this OGN model that you can find in the scene number 6 visual model. And you see, I just added this line down the file. I will file open, 6 visual. What can we see? The same, more or less, mesh, right? Just it's completely grayed because the OGN model I did not give any texture or color or whatever. Therefore, it puts some kind of gray by default. And I will animate. Let me know what you see here. You see? We start to say, okay, we have another representation that will be this OGN model. But we forgot one thing to connect this rendering and the mechanics. Again, on the rendering, there is no computation related to the mechanics, nothing. The rendering model renders, that's all. But here, so far, the rendering model is missing the connection. This transformation that will keep the rendering model aware of the latest position, velocities of each of my node, of my object. It's what is missing here. Do you remember?
We should probably reload the node position at each time step.
Yeah, and something that will automatically do that because it will create a correspondence between the mechanical model and the rendering model. It's a mapping. We will create a mapping, so a connection between the two, and it looks like that here. What we usually do when we create like a sub-representation, like a rendering model, we like to create it as a sub-node inside the object, because the main is the mechanics. That's what we wrote so far. And the rest will be following. The rendering model is just following. So if we think in terms of hierarchy, it's some kind of following, and therefore we create it as a sub-node that I name here visual. That's my OGN model, which is still using as a source the mesh loader course, but you see, now we are one node, 2 nodes below. So therefore, there is a @ ... to go up 2 nodes above. Mesh loader course. We are connecting to the same mesh loader course, but this time we add a mapping that takes as input the mechanics and as output the OGN model. By doing that, the propagation, as you said, Guillaume, of the position and velocities at each time step is automatically done by SOFA. SOFA runs automatically updates of those new positions and velocities, also like for the rendering model. And if we do so, we'll have the scene number 7 mapping the lever that you have now should be some kind of a yellow lever. And now if I animate it, you see the mesh following. Let's look at the view here. Let's hide the visual model, and you see that the visual model is indeed following the mechanics. If I pull on the mechanics, the rendering model is following. Is following because the deformation, the motion basically, the motion of the object, the new position of my object are updated at each time step through the mapping. We were in a case here where the mechanical model and the visual model were using the same mesh. So we use this mapping, which is like identity mapping, saying it's the same mesh. Why? Because I have object 1 is equal to a transformation of object 2, or I have object 2, which is a transformation of the object 1, the rendering, which is a transformation of the mechanics. But in fact, they have the same number of nodes. It's the very same mesh. So we go from one space to the same space. So the transformation is just the identity matrix. So that's why it's called identity mapping. What happens if we use two different meshes? What's the first thing we need? We need another mesh. If we want to use one for the mechanics and one for the rendering, let's add another mesh loader. But this time, the MSH format from Gmesh here can support volumetric object, as we saw before. OBJ files, I don't know if you're aware, but OBJ files, it's only for surface meshes. So here, instead of rendering the whole 3D mesh and each triangle of the mesh, even inside the mesh, we will only render a surface mesh, some kind of membrane mesh, a surface mesh of our object. The mesh is called Lever Smooth OBJ. That's the one we will load. But the name of the mesh loader is called mesh loader file. Look at which one is loaded by who. Mechanics is still loading the mesh loader course, the volumetric one. While for the rendering, all that we need for the rendering is the surface to render. Nothing, I mean, we do not necessarily need the volumetric rendering of the inside. Here, for the moment, we just need the outside, the surface. So we connect to the mesh loader fine, but since the two objects are not the same, we will need to create some kind of interpolation. This is automatically done by this mapping called a barycentric mapping, computing barycentric coordinates, so that you have an interpolation of the motion of the rendering model based on the information from the mechanics. So you see, we really, again, find this bottom arrow saying when the mechanics updates its information, the mapping transfers this information, propagates this information to the rendering object, rendering a model, sorry, a rendering representation, which is here in a sub node of the node lever. Okay. So let's take a look here. File, open the 7 fine visual. Now we have this fine red mesh here. Let me do that here. If we put that as wireframe, I deactivated the force field. I only see the rendering mesh, and if I go inside, you see, let me go inside, it's only a triangulated surface. It's just one surface. While if I activate the force field, as you can notice, this is a 3D volumetric mesh. It's the same as the one we were using so far. So what happens when I run that? So I run the simulation, sorry. There. I then grab it again. And you see, even if the mesh, the red mesh that we have here, is not the same than the one used for the mechanics, the red mesh will move. Actually, an interpolation of the deformation, the motion of the mechanics which is here, the motion of the mechanics will be interpolated on this red mesh through the barycentric mapping. Okay? So this way, we achieved to have one part of the simulation which is dedicated to mechanics with the integration scheme, the linear solver, the topology, the mechanical object, and the physics, all working on this 3D volumetric mesh, the blue mesh here. And with some kind of attached to it, in the SOFA vocabulary, we say we mapped on this mechanical representation a rendering one, which is just a surface mesh, different, actually a bit smoother, onto it. And both now are connected. And I don't need to manually define how does the rendering model move and so on. It's automatically done, obviously. Okay. So we now have both. So if I want to get back to we now have both the deformation model and a rendering model. That's what we have now. In the examples that you have in the zip file, here, I added one other example, which is here, the 7 mapping extract surface. It's an example where we actually highlight how to, if we want, keep the same mesh than the mechanics, but instead of like creating a new mesh or so on, extract the surface of this one and use it, for instance, for the rendering. This is what is done. What is done in the scene number 7, extract surface, mapping extract surface. And as you can notice here, if I go in wireframe and I will hide the forces, you see the triangles at the surface, the green ones, are the same than the ones at the surface of the blue mesh. We just extracted only the surface of the mesh. Okay? Just so that you know, it's something which is possible with SOFA to avoid remeshing, creating a dedicated mesh for something, and you can just extract the surface if you'd like. Okay. So I will show you a few other details, and then we will move to adding the third and last representation, which is the collision. But here we already saw the two main ones, the two first ones, like the mechanics, the rendering, only one to go. Just before that, I'd like to show you a few details. For instance, so far, the object is completely free to move. In fact, usually we have some so-called boundary conditions to limit the motion, or at least to specify that some nodes might be attached, some nodes might be allowed to slide, that kind of things. To do so, one way is to use what we call projective constraints. Like one of them is the fixed constraint. This one has all the projective constraint. The fixed constraint, what it does, it projects at the beginning and at the end of the time step what it's supposed to do. The fixed constraint is supposed to fix some nodes, some degrees of freedom. So what it does is that at the beginning of the time step, the fixed constraint projects a 0 velocity at the nodes 1, 3, and 50. And at the end of the time step, once the resolution is done, and that we computed some new position, new velocities, most importantly, the velocities of those nodes, when the velocities have been updated, we project back again 0 velocity, so that we make sure that it does not move. This kind of constraint is called projective constraint. It's a bit, I won't say brutal, but it's projective, and yeah, that works. That works nicely, and this will fix actually the nodes with the indices 1, 3, and 50. Let's check that. Let me know if you have any question in the meantime, all right? Can you notice the 3 nodes here? Yeah, So that's the one. When you activate the behavior model, it will highlight the nodes that we specified here in the fixed constraint. Okay, the behavior models here, and we see the 3 nodes that we constrained. How to actually check that? In Java, we have the, you remember this guy, the geometry algorithm, the one computing the volume of things, I mean, basically being a toolkit for geometry. It has another feature, is that it has a widget visualization that will allow you to draw all the point indices. For instance, here we see that the point is the point number 3, and we can see that the number 50 is here and the number 1 is here. I can zoom in on the number 1 here. So that's indeed my 1, 3, 50, the 3 nodes where all their degrees of freedom, x, y, z, are projected to 0. Basically, they are enforced not to move, enforced to have a 0 velocity. If I animate that, which force is acting here on my object? Carolina, on this mesh, on this lever, which force is acting? Look, you can look at the scene graph here. Or I can move that here and you can check here. I can't hear you just in case, but you remember we have a volumetric object on which we are defining a mass density. We defined as well just above here the linear elasticity, so we know how it deforms, but this is for the material. What external force is applied to it? The constant force field, applying some nodal forces on the mesh. I can still render it if you like. It's here. It was in visualization. The arrow side is here. Sorry. There. There we are. We still see the constant forces applied to our nodes. But the fact is, those 3 here, 1, 3, and 50, we enforce a 0 velocity. So what happens? The constant force is pushing, maybe a bit like a gravity would do, but gravitational acceleration will be a volumetric force. Here we just have a nodal force. But the 3 nodes are keeping our object in place. It's just like it was attached. It does not prevent the object to deform, right? I can deform it, but those 3 nodes are fixed. So in the same way, so that was for fixed constraint here. But there is a very similar constraint that exists. I will apply it only on the node number 3, which is called partial fixed constraint, where you can specify what are the fixed directions that you'd like. So do you want to fix it in X, in Y, in Z? And here I'm going to say, no, I'm going to let the X axis free to move. Let's reload, zoom in again. Remember, the point number 3 is this one. You now see that the point number 3 on the side is allowed, but to move only along X. Velocity can be non-zero in X, but Y and Z are fixed. So basically, X here can move, but it remains here fixed in Z and Y. All right? So if, for instance, if I look like that, exactly in plane, I will notice, though I should go on the other side, I will notice that the point is fixed in Y and Z. It's not moving when I'm looking in this side here, almost in the Y and Z plane. All right, that's another kind of projective constraint. Yeah, here I'm gonna just specify here projective. Actually, it's specifying that because we have some other kind of constraints. We could specify that this point is attached maybe to another point or stuff like that. We have some other constraints, but those are actually solved in a separate method, which requires another animation loop. I will get back to it right afterwards. Okay. So another feature I wanted to show you is the gravity. We still did not really play with it, but what is gravity? You remember? G. Gravitational acceleration has to be multiplied with mass density, rho. And when you do the mass times the gravitational acceleration, you get the force vector due to gravity. So notice that it's a bit different compared to what we had before, because before we had this constant force field, which is a nodal force. It does not care about how, what's the volume of the object, how big it is, or what's the mass density of the object. It applies a force on the node. That's it. The big difference with the gravity is that gravity is something that needs to be, again, integrated in space. But otherwise, the gravitational acceleration is a volumetric external force field. It's a field of force that will require the integration of the mass density, but otherwise, we compute m times g, and we get the acceleration, the gravitational force. Sorry. What I wanted to show to you here is that if we open the scene number 9, gravity, I run it, it's the same as before. I'm changing, what we can see here in the view, in the view options here. But what I wanted to show you here is if I double click on the root node, gravity, I multiply that by 10, it will change automatically the amount of force applied to my node. Get back to -1, or I can even go to like plus something positive, so it will push up here. So it's really a volumetric force applied to our object. Usually, definitely, gravitational acceleration is not changing, right? You're defining that once up in the scene, and then you do not change it. Theoretically, it does not make really sense. I think we are not making any kind of space shuttle simulation or whatever. So far, change of gravitational acceleration is not of interest. Just to show the fact that this applies, gravitational acceleration will apply a gravitational force to all the objects that have a mass. Okay. One last thing before moving to collision to the collision detection in SOFA, and maybe beforehand a break and a small session for questions. But look at the line with the tetrahedron, finite element method force field. So the one which is in charge of the computation of the linear elastic model, so the constitutive material model, the constitutive law, sorry, the mechanical constitutive law. And I will change this line by another one. Do you have an idea what this stuff is doing? What's the purpose of this component? Instead of having a component which is computing a linear elastic material, what does this guy do?
So this one is non-linear?
Nope. Look at everything is in the name. It's only a spring model. So instead of defining the fact that you are having like a continuous object that will require the integration of some mechanical law using parameters like the U modulus, the Poisson ratio, here, what we say is that, oh, don't bother, just put some springs on the edges. This kind of model is called a spring model. It's a very basic model. It's a linear model, yes, but not integrated in space, right? It's a very simple model, just putting some springs on the edges. Is that okay? You just like
it's applied on the edges or on the nodes?
On the edge. I mean, the edges are the springs, and the forces will be applied on the nodes. Everything at the end of the day always happen on the nodes. But where are the springs? On the edges between each node. And therefore, if two nodes are going apart from another, you have an attraction force applying due to the spring. You know, linear force depending on the elongation of the spring. It's a very basic model, a very basic model. But what I wanted to show you here is that with one line, it's an advantage. We have like about maybe 15 lines of XML here. Quick, easy to read, but easy to mess up, right? If you misread or type the name of something or whatever, you can have another model like this one. In one line, you are actually changing completely the mechanics. So what I mean in this slide is two things. It's first, this highlights what we said before, that in just a few lines, we can describe a simulation. In just one line, even sometimes when you change this line by another one, you are completely replacing the mechanical model that you defined associated to your object. But this, you know, as Spider-Man likes to say that, big powers brings also big responsibilities. It means that, you know, if you have just a few lines of code, you need to pay specific attention to each of the lines you write, because behind those lines, many things happened. So we just need to pay attention to what we write and so on, and what we do. All right. We achieved so far the deformation model, the rendering model, and we'll see now the collision model, the one used for collision detection. Is there any question to everything we saw? Yeah, we'll make a break anyway. I don't know if it was your question, Carolina. Anyway, if you have a question, please go ahead.
Sorry. So the spring model is like all the body has the same elasticity, but when we use Young modulus, for example, we can like this section with this Young model and this, it could be that the difference or no?
So I will reformulate your question to make sure that it's what you mean, but I think your question is, can we make things heterogeneous? Is that what you mean?
Yes,
to have some stiffness somewhere and some higher stiffness somewhere and lower stiffness somewhere else in the same object. Is that what you mean? Or
yes, so if we use the spring model, it's like the same, and that would be the difference or not? So
here you see that there is a list of springs. That's all the springs of the mesh, about 900 springs, and everything is defined. The rest length here, the stiffness. There is some damping that can be added, and some stiffness. So the stiffness of the spring. Actually, this component can add both a spring and a damper. It can add both, but it was not the purpose of my example. But you can manually specify each of those springs if you'd like, or define regions of springs if you'd like. And the same actually happens. So that was just to show the simulation running, the one with the springs. See, it works as well. It's just a different model, completely different model. It's not something which is volumetric. It's only lines, as you can notice. It's only springs and dampers along the lines. And what we had before was this guy here. There. Sorry. There we are. We had a volumetric object with a linear elastic model solved by integrating over each of the tetrahedron. We were integrating the mechanical model. So in the previous one, we could define the stiffness on each spring, and actually on this one, if you go in the tetrahedron finite element method force field, which corresponds to the linear elasticity force field, you go in properties. You have here, you have here the Young modulus. So I think you can either specify the Young modulus as, let me check here. Yeah, you can specify the Young modulus as a vector. I don't know if you can see that here, vector of doubles. It can be either one entry and it's going to be homogeneous, or it's a vector for each tetrahedron of the mesh. So it will be a vector of the size of the number of tetrahedron, and you can specify which Young modulus for which tetrahedron. Okay.
So you show in the spring parameters that it's including also the damping.
So it's including a basic damper model on the edge. Damping, damping is another, like it's a way to add the damping on the edge, but it depends on what damping do you want to add.
Yeah, okay, it's maybe not the best models for damping.
It's a basic model. It's a really here it's really a basic spring damper model. You have, it depends on what you want to do with and what you mean by damping. If you want to have some physical damping, you know, a material, it means that you want a material which is viscous.
Yeah.
A viscous material. We recently had actually a plugin that has been implemented by someone from Belgium to be able to define viscoelastic material.
Okay.
So that does exist.
Way better.
And that does exist in SOFA. And there is something else. Sometimes people are looking for damping in terms of numerical damping so again, it's back to numerical analysis to stabilize the simulation or to help convergence of oscillatory motion or stuff like that. So it's something else. It's called Rayleigh damping, but it's another kind of damping. It's a numerical damping to damp the mechanics of your object, but it's some kind of faking it's a fake damping. So it's something else. So about damping, it all depends on what you want to achieve. A physical damping, like your material is viscous. In that case, again, it would be the viscoelastic plugin that I mentioned earlier, or if it would be more to stabilize the result of a simulation.
Mm-hmm. Okay, I see.
All right. Any other question? We can make a short break here. Let's say we can restart at in 8 minutes, so that we can restart at 50. If it's good for you guys, we will do the collision detection. We'll move to Python, and we will conclude again on the math to the code session. We'll see if we have some time for this session. What matters the most, I think, is really the user tutorial. Okay.
Okay, great.
See you in 7 minutes.
Okay, see you.
Okay. So we had so far deformation, mechanical model, rendering model. We'll add now the collision model, the model used for collision detection. As I said earlier, that we have a collision pipeline coming by default with SOFA. It's working in 3 steps. You remember the broad phase, where we check whether bounding boxes are intersecting. If they do, we get closer. Using the narrow phase, we take a closer look, and we will use these proximity intersection methods to check if the proximity, basically the collision model, of one object is intersecting with the proximities, the primitives of the other model. And if they do, we will create a contact. To do so, we need to add a collision pipeline. A pipeline, the collision pipeline, it's some kind of the whole process, the whole loop, the whole step for collision. And when adding it, we firstly add a collision pipeline, which is the guy responsible for the steps to be computed within the collision path, the collision substep. Does that remind you something? It's a bit like the animation loop, but just for the collision. It's some kind of the sub-chief. It's listening to the default, to the animation loop. And when the animation loop throws the orders that it's time to compute to detect the collision, this is the collision pipeline who receives the information and then takes the lead and will compute the 3 steps of the collision detection and collision response. Okay, so this guy has an animation loop, the collision pipeline. It does nothing. It just defines the steps. 3 steps, broad phase. Okay, you have one here. Brute force, checking the bounding boxes. The bounding volume hierarchy BVH, so we'll build actually a set of boxes and a lot of sub boxes to identify if the big bounding boxes intersected. We'll firstly locate where it occurred, if there is a contact, and then using the proximity intersection, we will check model per model, primitive against primitive, if there is a contact or not. Like before, if the sphere was colliding here, if the sphere was colliding with the surrounding triangles here. The narrow phase, BVH narrow phase, allows us to very precisely locate where may happen the contact, and the proximity intersection actually checks it. Checks if there is or not intersection. What's the last guy? The name is in it. It's the guy in charge of the response. You remember that we have two types of collision response, either with penalties and the other one was with constraints, so-called Lagrange constraints. In this tutorial, we will mostly focus on the penalties because actually when we use a default animation loop, the only response we can use is this one. Can only use penalties. Penalties, you know, they check how much intersection there is, how much the contact has been violated somehow. We take this distance, we apply a stiffness coefficient, and it creates a spring force repulsing the two objects, one from another, to avoid the contact. This is a so-called penalty. So it's something which is pretty weak, because it does not ensure that at the end of the time step you avoid contact. But that's one of the two methods. And that's the only method that works with the default animation loop. So that was for the different methods that were available to you. And this is documented here on or actually everything here is documented in the user documentation to know more about the direct SAP, about the mean proximity, local mean distance, and so on. So broad phase, there is only, I think, only one. Narrow phase, you have BVH narrow phase and direct SAP for sweep and prune. It's another method, but which both aims at finding the location of the possible intersection. And finally, using both meshes used for collision detection, we will check pairs to pair of primitives if there is intersection or not. And then it creates a contact. So we saw that we need a small block of five lines right after the default animation loop to define the collision pipeline. But then we will be able to define for each object what representation, what kind of sub-representation we want to use as a collision detection model, as a collision detection primitive. Exactly as before with the rendering model, if we take the example of the node lever, what do? We create another sub-node, not for the rendering this time, but for collision detection. We can choose which mesh to use, and that will be used as primitive for collision detection. In that case, we specify that we will use the triangle as collision model. And exactly as for the rendering, we will connect the collision, the collision model, so the mechanical object that was here, storing forces, to the ... means we go one node above and we take the mechanical object. It's exactly the same as writing at ... mechanical model, because it's the name here. Okay? Basically, the input is always pointing to the mechanical object of the mechanics, right above. If I was going to the next slide here, I would really skip and consider that, yeah, that's okay, it's obvious here. I mean, no, it's not. We have a sub-node collision, okay, for the sub-representation of collision. What is mesh topology so far? I did not really mention what this guy is doing. I don't know if you can guess. It's pretty simple. The name is a bit in it. Why is there a mechanical object? Because for the rendering, there is none. And I think collision model is pretty okay. It's basically the primitives that we will use for the collision detection. Okay. Do you have any other question? Otherwise, I will answer the two first questions I asked to myself. Do you have any idea what is the mesh topology first? The mesh topology is exactly as a topology container, the set topology container that we saw before. But it has one big difference, is that the set topology container is able to update, so possibly the topology can change. The mesh topology, it's a static topology. Okay? It's a topology that once it has been defined, cannot change. So you cannot cut the object, you cannot tear the object apart, the topology must remain unchanged. If your topology is never changing, just use the mesh topology. But as for the topology container, we use the SRC, the source, and we catch all the information from a mesh loader. Here we use the same mesh for the collision model. We use the same mesh as the rendering. So you remember this smooth mesh, the smooth red mesh, this is the mesh we will use for the collision detection. And second question, why do we need, you think, a mechanical object? The answer is here. The answer is around here. And the answer is exactly here. In the case of a rendering model, I think we agree that the rendering model don't give a damn about the mechanics. It's only here to render. It's completely passive. But the collision is not the same. The collision is obviously, we want the mesh to follow what happens with the mechanics. But the collision will save some information about the contact. And it needs to provide this information, whether it's a force or just the distance of interpenetration, back up to the mechanics. And then the mechanics does whatever she wants with it, but we need to do something with it. That's this bidirectional arrow. This bidirectional arrow, that's the mapping still. But indeed, we propagate the new position and velocities v from the mechanics down to from the mechanics to the collision detection. But as soon as we have some collision detection force or collision detection information, we want to propagate that back up to the mechanics. And if you remember, the animation loop, default animation loop, is in 2 steps. And therefore, we will store some collision detection, especially if we use penalties. We will have some spring forces that we can compute. But the physics is not yet even computed, neither solved. So we need to temporarily store the force information from the contact. This is why we need this mechanical object. Then the mapping will take automatically this force and propagate that back up to the mechanics. It's automatically done. And what's, on your opinion, this contact stiffness?
It's overlapping between the two components, maybe.
You remember, if we have a contact, we may have somewhere some intersection. Therefore, the 2 objects are going through another. So we have interpenetration. We have a violation, a distance of interpenetration. And I said penalties. We take this
spring.
Exactly.
Okay.
It's the spring, it's the stiffness of the spring that we will apply depending on the violation distance of the contact.
Yeah. Excuse me, can we step back on the
different
step to just to clarify for me?
Mm-hmm.
So in the collision calculation or check, so I suppose first there is a check between the overlap or the collision between the 2 volumes.
Yeah, the 2 bounding boxes. We compute bounding box like a box which is surrounding the object, a box which is aligned along X, Y, and Z. This will allow super quick computations between 2 boxes if the boxes are intersecting or not.
So let's say you have a 1 millimeter intersection on a point. So you determine the new. So you correct your model with this 1 millimeters, and you apply the spring.
So what happens in the case of the penalty? So that's what we're looking at so far. So the first step would be if there is collision, as you said, from 1 millimeter between maybe the triangle and the sphere that we have here, let's say. It means that firstly, the 2 boxes, bounding boxes, would intersect. Because it means the 2 objects are intersecting somewhere. It means the boxes need to intersect somewhere for sure. So we would straight away go to the narrow phase. The narrow phase would detect this 1 millimeter interpenetration using the proximity check. We would indeed confirm that the sphere is violating from 1 millimeter the contact with the triangle, which is, for instance, this one here. What happens here at the end of the collision pipeline with the collision response is that still in the animation, we're still in the first step, collision detection. At the end of this step, what does the collision response? It creates a spring with the stiffness that we specified, and it will automatically generate, therefore, the force of, in our case, it was here 3 times the 1 millimeter. So it should apply a force. If we are using SI unit, it means we should have a force of 3 to the power of -3, right? And this force will be taken into account when we solve the physics, because the mapping will propagate that back up to the mechanics. But to get back to exactly the point you were pointing, I think, Guillaume, we apply a force on some nodes, but we don't move those nodes. We just apply a force. That's what I meant about penalty approach, that we apply some forces to try to prevent from collision, but you have no insurance that at the end of the time step, you succeeded to actually repulse applied a sufficiently high force and not too high force on your nodes to prevent the contact. This kind of force is a bit, especially because we manually define this contact stiffness, is very sensitive, very, very sensitive. You might not be able to prevent the contact, and you might also sometimes apply a force which is way too high, depending on the value you are putting here, depending on the velocities that objects are coming against each other, and so on and so forth. So it's sensitive to tuning. Okay, I will comment again on that later on. So if we open the scene number 11, I think it's basically the entire scene. Now you see that we have a collision model, but we have as well a rendering model. We have as well a force field, so a mechanical model. If I run the simulation, it deforms. The rendering model follows through the mapping. The collision model follows through the mapping. The pointing down arrow is propagating indeed the position and velocities coming from the mechanics, right? Here, what I'm moving is only the mechanics. All the rest is following. What is missing? You remember our rigid sphere? Let's add another object. And why not reusing exactly the exact case we had before? Just a rigid particle located in some places. We will apply a force so that it's pushed against the lever. The only difference compared to before is that I'm directly adding a collision model. Since we have only like one frame here, I mean, since it's actually a rigid body, a rigid body here, we can simply here put sphere collision model. The sphere collision model add some spheres on each of the node. It's a very simple collision model. It does not care about a mesh. It takes the number of nodes and put some spheres on it. That's what it does. Here we have one rigid frame. So it puts one rigid sphere around the frame, the rigid frame, and this sphere will be used for collision detection. Okay, so it looks like that here. It looks like that here. It's the scene number 12. If I open it here here, it's a 12 collision object penalty. I have my default animation loop. I could remove that here. I have a collision pipeline in charge of the first sub-step of the animation loop, the collision detection. It will check the broad phase, bounding boxes, check the narrow phase to identify using the sub-boxes where exactly the contact occurred, and using the intersection, computes the detection output saying, okay, the contact occurred here with this distance of interpenetration. And what does this guy? It's creating some spring forces if there is a contact. What I did not mention is the contact distance here. That's the most important one. Alarm distance is just for checks, but when objects are coming fast close to another. But this is a distance below which you will consider there is a contact. It means it's some kind of layer, a fake collision membrane offset that you create on top of your surface. Here, 0.25, some kind of safety margin. And we will apply, so the penalty force field, so the penalty springs. The coarse mesh for the mechanics, volumetric mesh for the mechanics, and the smooth surface mesh that we will use for what? For the rendering and for the collision, as before. Just I added one thing here, is my sphere that will fall onto the lever. I placed it exactly in -2x plus 10 y 0z, so that it's above my lever, and I'm pushing in. This is y, so I need to push in minus y. This is y. Here I got 0 minus y 0 minus 1. Sorry, 0. Let's run that. As you can notice, they did not, went through another because we have this safety margin of 0.25, but we had a contact. One is bouncing over the other one. Okay. Let's check more in details what exactly happened here. I will click on the interactions option in the view widget. I will run the simulation and I will ask you to pay a specific attention to the sim graph. As you might have noticed, I have both here a line that appeared and two objects, two components that appeared in the graph. One is called barycentric penalty contact. The other one is called penalty contact force field. This is a component in charge of applying spring forces on all the interacting objects, on all the colliding objects. There is more than that happens dynamically. Let's check the collision node. So for those who know Tintin, you know that's Captain Haddock way of healing, but so it's random names that has been given to some component. Look at the right. We in the collision node of the lever, we created actually the collision response, created a subnode with a mechanical object and a collision mapping, barycentric mapping. Sorry, barycentric mapping. What do you think this guy is? We created a subnode in the collision representation, and this node contains a mechanical object. Mechanical object. The type is vec3d, like the lever, same type, and a barycentric mapping. So we are mapping, making a correspondence between this mechanical object and the collision model. I will like visualize this point because it's actually only one point here. Can you see it? I thought maybe not unread, but let's. Can you see what is this point here? So far, before creating the spring, identified on both objects, so here it's the lever, in the collision node of the lever, it identified where is actually exactly located the contact point. As you can notice, I will zoom in a bit. We'll zoom in a bit, like I need to, sorry, yeah, there. And I will go wireframe.
Does it create a new surface or it take what is available on the model?
Yeah, no, it keeps the surface that we're using as a collision primitive, like the surface made of triangles, the yellow one that we see, but it just created one new point and he's mapping this point. So he's basically referencing, explaining where is located this point on the surface. That's what does the mapping. And this point is the projection of the point of contact.
Okay.
Because you remember, I said there is a bit of offset between the two. So basically the contact occurred somewhere here. There is an offset between the two. And we have the collision point for the lever object, which is here. And if I check for the sphere, it will be the same. I have as well a collision point, a point of collision projected on the surface of the sphere, which is here. Why? Because the force will be applied here for the sphere and here for the lever. Actually, that's the contact point for each object. Okay? And this is dynamically created. And what will happen is that The force will be, so you know, there will be a normal force due to the spring. A force will be applied because a spring will be set here between the two. The force will be stored here in the mechanical object of the contact. You can notice that's the force, amplitude, and direction, the force amplitude in X, Y, and Z due to the contact. It's basically the distance of interpenetration times the value of contact stiffness that we had. Okay. So.
Sorry.
Yeah.
To compute this point, it actually computes the nearest point to the sphere, right? The nearest point on the other object to the sphere.
Yeah, exactly. Yeah. So using the triangles, the triangle collision model, so the triangles on the surface, it will pair. So it will take the sphere, take one triangle, check if it's the closest one, if there is contact, and if it's the closest one, take in the reason and take the point, the real point of contact, create it under the collision node, map it, and the force of contact is defined here because the force of contact happens at the point of contact. So that's where it happens. And then when it will be time to solve the physics, what will happen? Because this point is not existing, not even on the yellow mesh of the collision detection. It's a point, it's a random point somewhere on the surface, but not necessarily one point, one of those, one of those nodes here, like here or here, it's another node. So it's interpolated using this barycentric mapping. So the force, which is here, needs to be interpolated here on the yellow mesh here. Then, to be taken into account for the mechanics, it will be again interpolated using the barycentric mapping, projected back up to the mesh, the blue mesh. You remember the mesh used for used for the mechanics on this mesh here. So we have two mappings in a row that will compute finally the force on the mechanics. We have the point of contact. We map the force of the point of contact on this triangulated surface. One point mapped on the triangles. How many nodes of the triangulated mesh here will have some forces? We'll have 3 nodes. Actually, since the point of contact is somewhere on a triangle, right? So somewhere on the triangle, if we interpolate the force at the nodes, we will have 3 nodes that will undergo a contact force. And we can find those 3 nodes here. So here we have a lot of nodes which have 0 force, but we will have 3 nodes. I don't know where they are. Here is one of them, which I just missed it here. Here is one of the 3 nodes around the point of contact. So the force is interpolated around those 3 nodes and up again on the mechanics. Okay? So again, and just to remember, I activated, it was a bit short before, the interactions option here allows you to check here. You know you have some lines appearing, and it shows you whether there is a contact or not between the objects. Okay. And then this contact force will push the rigid frame. And I tuned the collision parameter so that the penalty method works well in that case to repulse the rigid frame, and it will also create a motion on the lever. Okay. So with that, we achieved a penalty-based collision detection between a rigid frame and a deformable object. I'd like to show you just one other stuff but here I'm going to make it very short because it's, you know, the other method, because I guess you can feel it right now. Penalties, I already said it, it's very sensitive. You need to tune them, especially this contact stiffness parameter. And it does not ensure that at the end of the time step, your contact is actually respected and objects are not intersecting anymore. They can be in contact, but not through another. Here, we have no way to actually check to make sure that this works. Let me give you an example. Let's take the very same scene and where is my collision here? I will decrease the stiffness of those collision penalty springs. What happens? I will play that one last time. Check the scene graph. Collision is detected. The spring is there. The force is applied. But I'm actually multiplying it by something which is now very small. So the contact force is very small. Not strong enough to repulse a rigid frame, which carry on because of the constant force. It continues to go down. It will go through. It will just go through another because the collision did not succeed to properly respond to collision. The tuning of the penalty force field, for the penalty forces using the penalty contact force field is not correct. This is the kind of manual tuning which is enforced using the penalty approach available in SOFA.
How can we link this contact stiffness with the real value of the material? Is there a rule or?
It's something that will be, it will be something that will be really relative to the property of one object and the other one. And actually, on my point of view, it's like mostly fine tuning that you need to do to have something which at least looks realistic. And this is why. This is the reason why when we use this collision response with penalty contact force field, we need to have this contact stiffness. This is easy to set up and it goes pretty fast, but it's hard to tune. It's actually adding energy to the system, something that we like to avoid usually. It does not work with haptic feedback. And this is why we were looking for an alternative method for avoiding tuning, taking into account also the mechanical properties, because that's what you asked, Guillaume. How can we relay that somehow to the mechanics of this? As is not possible. We are actually working currently on implementing more, I would say, aware methods of penalties, because there is better ones that can be implemented. And something that still could be efficient. This is the other method. I told you there is penalties and there is collision detection, and there is collision response using constraints, so-called Lagrange multiplier constraints. This requires something a bit more complicated. We have a dedicated course for that. I think it was related to what you said you wanted to discuss also with the defrost team, Guillaume. It's something that we can definitely help for, like covering and understanding. But as you can notice, the animation loop, the steps that have to be computed within one time step, are not anymore 2 steps. There is resolution of the mechanics without contact, collision detection, not response straight away. First, we solve a constraint problem to find the exact forces to be applied so that at the end of the time step, the mechanics is respected and the contacts are fulfilled. The constraint law is fulfilled. It means we are not intersecting anymore. And when we converge towards a solution, we apply those new contact forces, the so-called Lagrange multipliers. So it's a 4-step method, which is a bit more complicated, and therefore, since we don't do the same step and especially not in the same order, we have another animation loop, which is the free motion animation loop dedicated to constraint problem. So you see, it's that kind of scene. You see a different animation loop. Obviously, the response is not anymore using penalties, but using, actually, it's contact constraint. It can be friction or frictionless, but the friction contact constraint handles both friction and frictionless. You will need a constraint solver. The most generic one, the one that handles any kind of constraint, is the generic constraint solver. And for each object, we'll have to define the way we want to correct. It's the fourth step. There is different approaches for that. We need a constraint correction. So you see, the scene has to change a bit as well when we want to use these Lagrange multipliers. But no need anymore to define a contact stiffness. I created, let me check that here. I created on GitHub on the, you remember I mentioned that at the beginning of the session, the forum. Here, I think it was in ideas, suggestions. So yeah, that's for rigidification. Yeah, and I made a very, very small post on the usual errors that people do when they're moving towards Lagrange constraints. When they were using penalties and they want to use Lagrange constraints, this post here, the 4173, details a bit the things to be done. Otherwise, you have a full documentation page on really what are those Lagrange multiplier constraint resolution, how does it work, the whole equation, and so on, if you are curious. But otherwise, again, we could cover that in a, but it's actually important to cover that in a second step. As you can notice, the course of today is like a broad overview on how to build a simulation. We can dig more on each of the topics: collision detection, constraint resolution, the mechanical constitutive laws, and so on and so forth. All right. I'm checking the time. So on my end, I would need, if it's fine for you, I would need to leave a bit before 5, so in an hour and like 20 minutes, so that yeah, I got a daughter to pick up today a bit earlier. Usually I do trainings to my place. So do you need a break? Because we could do a very last break right now, and then we do a straight line up to the end. If there is questions about collision detection for some of you, you can stay and ask the question. Otherwise, we can say that yeah, at 35 we can restart if it's fine for you, like in 4 or 5 minutes, just the time for a short break, and then we restart. Is that okay?
Yes.
Cool. I'll stay here. If you have some questions, I can stay definitely, and we can. I would happily answer them, and also after the break. See you in 4 or 5 minutes. Yeah. See you. Were you able so far to run all the simulations up to the simulation number 12 and even 13? 13 was is an example of the very same example, but instead of running it with penalties, you have the Lagrange example, and you'll see basically the same collision detection, but using Lagrange multipliers that will do the detection, the computation of the contact forces, and so on. Were you able, with the software version that you had all at your place, to run this scene file so far? Yeah?
Yes,
yeah? Okay, cool. So now, for the one of you who like like if you installed Sofa, as we said, if you have like, I think for the Windows guys, if you have like the Python version 3.8, as we said, you should be able to do what I will show you. I won't do it myself because I would like to show you the two ways of doing it. So you can go in Edit, Plugin Manager, and here, if we want to work with Python, we'll need to have the Sofa Python 3, so a plugin for Python, loaded in Sofa. So what we will need is in the binary version of Sofa, I need to find my binary version of Sofa. Here, I installed my v23.06 Linux version. And in plugins, I will have a list of plugins available, including the Sofa Python 3.1. So I will open it, and I think on Windows it will be in bin. You will have a DLL. On Linux, it's in lib. You have the .so. So it should be lib Sofa Python 3.so, and you should be able to load it, or .dll for Windows. Can you let me know whether this works or not for you? So I can do that again. Edit, Plugin Manager, Add, and then here, go to your binary version of Sofa at the root, not in lib, but at the root. And then you go in Plugins, Sofa Python 3, and in lib for Linux and in bin for Windows. You should have in bin the DLL, and on Linux, in lib, the .so. And by clicking here, if you have the proper the Python 3.8 version, you should be able to load it properly without a warning. I see, Ronak, it's working. Guillaume, is that working for you too? And Carolina as well?
So actually, I don't know where is the install the software. So I look into
okay, all right. It's yeah. What for you, Carolina?
What was the question?
So are you able to like load the Sofa Python 3 plugin? Yeah. Okay, great.
Yes, I got it. Yes.
So while you're looking, Guillaume, another way of doing it is once you've done it using the plugin manager, you won't have to do it again. Okay? It has to be done once and then it's done. On my end here, if I'm using the command window, what I can as well do, here I'm in the release binary version of Sofa. And what I can do is to specify with a -L what are the dynamic libraries that I would like to load for Sofa. So in plugins again, Sofa Python 3, lib, and lib.so here. And by doing that, I will be able now to load Sofa training scenes. In the training scenes that I sent you, I will be able to load Python scripts, py files. So here, if I do that, it works. If I just write, so if I just do this, if I just do run Sofa and the py scene, what does Sofa tell me? Error, I don't know what is a Python script. Please load the Sofa Python 3 plugin. So when you see that, it means run Sofa, the executable version of the executable of Sofa does not know Python, therefore it has no Sofa Python 3 plugin loaded, properly loaded.
So what's the name exactly?
So it's in plugins, yeah, in the
Sofa Python 3.
Correct, and then bin for Windows, and the DLL.
I mean bin.
And the DLL. There should be lib Sofa Python 3 DLL.dll.
So I have your library loading error. Couldn't be fine.
Okay, so I guess since you actually loaded the proper one, because I know you're having the Python 3.8.10, I think, you are having this version of Python, which is the one we used for the release. There should be no problem. So if there is a problem, it means it might be a write problem, a problem of write access, access to the library as a user. I'll show you anyway what we can do. So could you, in the meantime, Carolina and Ronak, run the same things as I do, so that you can test the scenes yourself? I'll show you now. It's time actually to see the difference between XML and Python. You remember of this scene file? It was the scene number 3. Yeah, I see Carolina is recognizing it. It's basically the rigid particle under a constant force. If we open the scene number 3 with the run so far, it was the scene file that we had before. Okay, how does this very scene look like in Python? If we want to create a script, look here for run SOFA, for the executable of SOFA. All that you need to do is to write import SOFA runtime, the Python libraries of SOFA for Python, and just one function called create scene, as I said a bit earlier. This create scene function takes as a variable root node, and this is obviously the pointer towards the root node, and we can, from here, do whatever we want, give a name to the root node, set up the time step, define the gravity, add a child node, add in this child node objects, and then if we do that, it will create. You see, we have the name of the component, and after, what's that again? Carolina, what's the name of those guys here in SOFA? How do we call that? Template, name, position. These are, the parameters of each component. Ronak, you said it earlier, the data. Yeah, that's all the data of the component. For instance, the data of the component mechanical object here, template, name, position, and show object. So we define the name of the component and all the data we want to specify. So it's very similar to here. Just as you can notice, we have some comma in between here that appears. That's it. Okay? So here we can use actually Python booleans, false, true. Here we can use numpy vectors and numpy arrays and stuff like that, like for gravity here. And this script, if I take this one, it's the one number 14, more or less. The one number 14, you can do run SOFA, my script, and since you already loaded the SOFA Python 3, it will work. On my end, I will do that here. I will do what is written here. I will manually load the library, but if you loaded it once using the plugin manager, then you're done. It's once and for all. You're free to. So what do we see here? Can you have that as well, like Carolina and Ronak? Yeah. And if I animate, we'll do that again, and again, and again. It's the very same example as we had before, a rigid particle in 0, 0, 0, which moves a rigid frame pushed along the x direction by the constant force. So you see that whether it's in XML or in Python, it's the same. Okay? Okay, so you can tell me, nice, okay, that's XML, Python, same, okay, what's up? So the big difference is that this script, if we update it just a bit, we can run it also from a Python environment. To do so, if you go on the documentation of SOFA here, Chuck, you go on Python 3. Okay, it doesn't find immediately. So plugins, usual plugins, Python scripting, SOFA Python 3, and you see there is a read the doc here in the SOFA Python 3 section of plugins, usual plugins, Python scripting. And if I click here, it brings me to the documentation of SOFA Python 3, and especially how to set up a Python environment. You know, all the like Python environment is a specific environment, and what needs Python to know? It needs to know where is SOFA. If we want to use SOFA in Python, we need to specify where is SOFA. So there is on Linux to export to do the export of the location of the install of SOFA, the binary version of SOFA, and as a variable called SOFA_root, and export Python path, and here the path to the SOFA Python 3 plugin, lib, and Python 3 side packages. It's those side packages, it's the Python library of SOFA for Python. As soon as you give this here, you will be able to run simulation from SOFA within a Python environment. What does that mean? So, you know, you'll have to export here the SOFA root, and here specify where is the SOFA binary. That's the path to SOFA. And again, the other one is Python path, and add to this Python path the path to, in our case, it's located in ls plugins SOFA Python 3 in the binary version of SOFA, lib, side packages, and lib Python 3, side packages, and here I give this path to SOFA Python 3, to Python path, sorry, and Python will be able to find SOFA. By doing so, all the instructions again are online here on for Ubuntu, obviously. For Windows, it's the same. You just have like two additional variables to set up in the environment, but that's it. No worries. The scene I'm gonna trigger from Python. You can launch them also from run SOFA, obviously. So I just did that here. I triggered run SOFA and I opened the file, which is the scene number 14. But by adding just this main function here, which is called if we are in the Python environment, if I add this main function, I will be able from Python to use and to run SOFA. What is this function added? Can you guess what it's actually adding here? So if we're in Python, it calls main, and main then will call the create scene function that we defined earlier. But what is done in addition to this create scene function? What is done? First, the first line, we create a root node in Python. And the second, actually the third line after creating the scene, we initialize the scene graph. Why do we need to do that in Python? Because this is usually done by who? By the graphical user interface of SOFA, which is creating a root node for you and which is initializing the simulation for you. So here, since we are in Python, Python is like not aware of anything about SOFA, so we need to do everything for Python. Creating a root node, initializing the scene graph, and then up to me to do whatever I want. For instance, here I do a for loop 10 times, and I click on animate. So I trigger the animation 10 times. So I click on step, 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 step 10 times. So here I got SOFA running. That was with run SOFA, but I can therefore, it was, I got it, sorry, look. It here, I can do the very same, so not the 15, but the 14. So I'm triggering the very same scene file, and you see it's doing 10 time step for me through Python. Let's take a look at the scene file itself. The two imports to run so far from a Python environment. As before, the create scene function defining what is in the scene graph. AnimationLoop. We create a subnode. Integration scheme, linear solver, the degrees of freedom stored in the mechanical object, and the mass and the constant force. And we have a main function, which is creating the root node, initializing it. And when I'm in Python, you see, we do 10 iterations, and then we write simulation made 10 time steps, dot, done. This is what appeared here. So we can run a simulation from run so far or from a Python environment. So far, not much exciting, but let's get excited just a bit as a conclusion. So it's going to be a bit less than so the last hour. Let's take a look about what we actually can do with Python. First, the first frustration that you might have, if we look at the scene number 14, is that we were able to create like a simulation and to make 10 time steps, but without having access to any graphical user interface. So if you'd like, there is an example, the scene number 15, that does exactly the same, but instead of making 10 time steps, we open the graphical user interface of SOFA and we run the simulation in run SOFA. So the scene number 15, here, there is no more differences compared to before. We have run SOFA, started from Python. I have my particle. If I run animate, okay, everything as before. So I can also have access to the graphical user interface from a Python environment. Sorry. But so really, so far, nothing new. Here, I'm going to start playing with it. You remember the name of the root node? Okay, root. The time step is equal to 0.01. And here, we are having the root, so pointing towards the root node. That's my root node. What I could, for instance, do, I want to access the data, I have to just do write dot value. So if I do that, this should do it. Means when I'm gonna close my graphical user interface, when it is closed, it will tell me that it was closed, but here it will also print the time. I could have done that maybe a bit more. Time is this way. Okay. I will run again the script, run the simulation, stop it, and it gives me the time at the end of the simulation. You can say, well, okay, why not? Time of simulation. Actually, what I did here is that I accessed information from the simulation through Python, which means, okay, time is not really of interest, but if you're interested in the latest position, or if you like that at each time step you save the position and you make some processing, you can do it. Basically, in Python, you can access all the information you'd like. All the data are accessible. You can also access like the matrix of the system, the stiffness matrix, the mass matrix, the entire system matrix, to make some processing on top of it. Okay. Examples are also given and available for that in the SOFA Python 3 plugin. So that's typically the kind of things you can do. And I never did that myself, but we should be able to, if I take back the example number 14 here, and I'll take that again. I do that here. What am I doing here? I am rerunning 10 additional time steps after I close the graphical user interface. That's the kind of things you can really do. You have definitely with Python a direct access to SOFA, a direct access to all the data, to the component and to their property, those so-called data, access them and process them as much as you want outside from SOFA in a Python environment. Okay, that's the kind of things that can be done, and you will see little by little if we push that further and further, we can end up to like design optimization. If you want to optimize the design, you run a simulation, you export some data from your simulation and evaluate some values for your design optimization, restart another simulation, and so on and so forth. So that's the kind of things that can definitely be done in SOFA with Python. So yeah, that's for the link of the doc. Okay. And I'll show you two more examples of SOFA with Python. First, so that will be the file. I'm gonna trigger that from the Python 3 environment, but you can trigger and you can run it also from run SOFA. It would work the same. So I start the animation of this scene number 16. As you can notice, I open it here. The scene file is, the create scene function is here. As you can notice, the constant force is 0. So the particle that I'm creating is not moving. It's pretty logical. Okay. But I'm going to actually trigger some keyboard events by pressing the Control key and the plus key of my keyboard. So here, what I just did is I increased the total force of my constant force field. How? It's actually because I created an additional component here, as you can notice in the create scene function, but a component which is not like a regular SOFA component. You see, the way of defining it is not the same at all. We add an object, which is a function itself. Actually, it's not a function, it's a class. It's a Python class. And this one is defined just above here. And it's a so-called controller. Controllers in SOFA, that's component that allows you to interact with the simulation, have access to information when the time step begins, the time step is ending, when someone is pressing a key or moving the mouse or stuff like that. All those kind of interactions and events, you can listen to those events through controllers. And here, when I'm pressing some key, especially the plus key, I'm increasing the data, total force, of my constant force field. The detail of how does it look like in Python, we could take a look more if you're interested, but what is of interest here is to see that with Python, we can create, as before, a simulation. We can have access to data and process those data for post-processing, optimization design, as we said before, like analysis of your matrices and so on. But even while the simulation is running, I can access and modify data. Here, I'm modifying a force which is currently applied of my particle. It's still running here. Okay. It's still running here. Where is it? Okay, still running here. Oh, sorry. There. What I can do as well is not only so I can plus, minus, it's decreasing the force. I can plus again, it will push it again. But what I can do as well is adding objects. And here, again, we get back to what I said earlier about the Python plugin. It means you can access data, you can modify data even while it's running. You can create, so modify completely part of the graph by adding a new object, or, I did not do it, sorry, I could have done it as well, or destroying, that's very close, pardon, up, creating it here and removing those two. You can see on the left-hand side, the graph getting updated. I'm creating, deleting them, creating them, deleting them. I can do whatever I want with the same graph. So with Python, you can really, again, grab any information you'd like in SOFA, access it, modify it, create anything you'd like, or destroy anything you'd like in the graph, so that the simulation changes anytime you like, the way you like, and to have a maximum of interactivity. Stop here. So the detail of the example here is given in the script. You can see you have like the change in plus minus of the total force. And when I was pressing the A or the M key of my keyboard, so with always Control plus, Control minus, Control A or Control M, it was adding or removing particles. I don't know if you were able to do it on your end, by the way, Ronak and Carolina, were you able to like add and remove particles in the scene number 16, sorry?
Sorry, I didn't do that because I'm on Windows and it's running really slowly, so I just closed that. But I will do that on Ubuntu.
Yeah.
Yeah.
Okay. So, all right, yeah, and I'll show you one last example for Python, and then close this part here. Get back here, and I will run the very last example. You can take a look at it here. This is the scene file that we have. A default animation loop. We create one subnode. Linear integration scheme, linear solver, the mechanical objects storing the degrees of freedom. So it's it's actually not written, but by default, when no template is given, the one which is used is vec3d. If it was written, no, so it was not written. So vec3d. And what you can notice here is that you have 1, 2, 3. So it means 1 point. And you have a second point located in 1, 0, 0. So you have 2 points. Both points have, so they have a total mass of 0.1. Okay, why not? And this is a Python class. So we'll get back to it afterwards. I will remove it for the moment. If I animate, what happens knowing that gravity is non-zero? As expected, if I do have a weight, I'm on Earth, there is gravity, I should fall, right? There is, you are just releasing an object in the air, it will fall. That's what happens here. That's what is defined in my scene graph here. But I will uncomment this line, which is again not creating a SOFA component, but creating an object coming from a Python class defined again just above. And this Python class is, can you read what is here? The force field. I'm reading on Ronax Lips. Force field, meaning that it's going to apply some forces. A priori, that's the role of a force field. It applies forces. Can you tell me what kind of forces is this guy doing here, looking at the line in the function add force, which is adding a force, adding an explicit part of the force? What is that here? Initial position minus position, so current position, times a value. Initial position minus current position times a value. It looks like, what kind of object applies such a force? A distance times a constant. We are facing another spring, right? Initial position, current position, one minus the other times a constant. It means it's a spring that enforces the point to always remain at its initial position, right? But all that here is written in Python, as you can notice. All that is something which is not defined in SOFA. And even if we are fully in Python, I reloaded the scene. We have the two points falling due to their mass. But Python can not only allow you as a user to read data, access data, modify data while the simulation is running, modifying the graph while the simulation is running, but you can add physical phenomenon, implement physical phenomenon in Python. If you're not happy with that, and you would like to add some damping, how do you compute damping? It's based on the velocity. So let's say that the initial velocity is 0. So initial velocity minus current velocity. So we just keep current velocity. So the velocity is given here in the, you have position and velocity here. The velocity, we take velocity. And I prepared it a bit because we have a damping coefficient that can be specified to this Python class, and it's called KD instead of KS. So let's use KD. I save my Python script. I will reload and be prepared. We'll have not anymore a spring model, but a spring damper system. So you see, the interest is not doing a spring damper system. We don't care. The idea is more to show, to highlight that we can access anything, we can read anything, modify anything, we can even implement some kind of physics which is not existing at all in SOFA. If I want to create some kind of damping which takes the square of the velocity because I don't know why, it's possible. I don't know what, I never did it, but I guess it's going to be some kind of weird stuff. But it would work as well. It's another model, okay? So it's really to show the possibility that offers the integration of SOFA within Python to really access and I would say improve and increase the interactivity of your SOFA simulation through Python. That's what I wanted to address here. Okay. Is there any question for that part here? No? So I'm going to check exactly what, so we have, we have a bit less than like 30 minutes left. If we want to stop just a bit earlier. Okay. Okay, I'm gonna be quick on this very last part. It should not be any kind of rocket science stuff, okay? But as I said before, this part here will start to uncover the various fields that SOFA may cover. Numerical analysis, continuum mechanics, what did I say as well? Yeah, constraints resolution, that kind of things, okay? So we did the overview of the community, the user tutorial, and just for this very last part, I'll be quick and I don't want to push too strong on the theory. The idea is we talk about solid mechanics, okay? Solid mechanics meaning that whether it is deformable or rigid objects, we are looking for an equilibrium of forces. The equilibrium of forces is given by the Newton's law, coming from the momentum conservation law. The one that you know, and the one that we use actually to compute, what was the velocity of our rigid particle under a constant force, is the following one. We had the mass times the acceleration is equal to the sum of the forces. And what we saw together is both we addressed the case of a rigid particle and a deformable object, right? The rigid frame. And then we played with the lever that was deformable. It was an elastic, linear elasticity constitutive law. And that's the two cases we looked at today. So it will be the occasion of summarizing a bit what we saw along the day. Firstly, we noticed that we need an animation loop. Why? Because the animation loop is in charge of ordering what happens within one time step. We need to define one, and one is created by default, but I would really advise to specify which one of the two you want, either default animation loop or free motion animation loop. And as we just started to say, free motion animation loop requires a structure of the scene a bit more complex to actually be able to solve the constraints. And in the case of collision, to find the exact contact forces. Then we added the mechanical object. What we said is that it was super important to pay attention to the template to check what is the nature of the degrees of freedom that we're using. Depending on that, the field position is directly affected. And in the case of a rigid body, for instance, let's take an object which is rigid. We take its center of mass. We consider there is no angular velocities, no articulated system. Sorry, we take a single body, rigid body. We have external forces, internal forces. In the case of a rigid body, we just have external forces. A force, it moves. It does never deform. It just moves. But when you apply a force to a rigid object, it moves. We defined a mass and a constant force. You remember what was missing here? Yeah, sorry. What was missing here? We were clicking on the animate and nothing was moving.
I got the solver that was missing.
Yeah, the integration scheme, the one able to go from one time step to another, indeed. So I'll skip this part about the matrix here. I think we could cover that later on. Integration scheme and linear solver were indeed missing, because that's what allows you to, from the current state of your simulation, to go to the next one. That's typically time integration. For that, we need an integration scheme. That's what we did with the Euler implicit solver. The integration schemes allows you to go from x at the current time step to x at the next time step. And there is two families. I won't go into detail again today, but there is a first family, which is called explicit schemes. These ones, they actually, like mass times the acceleration is equal to the forces. The question is always, when in time, which x do I take? What are the values of my degrees of freedom should I take? Explicit ones, they will tell you, oh, just use values of x that you already know. For instance, the current position. If f, the force, depends on your degrees of freedom, x, use the one at the current time step. Okay, that's one choice. But you could use also like linear combination of those at the current time step and at the previous time steps. It's other kind of methods, just so that you know. But as soon as you use something which is known, so something from the past or the current state, it's called explicit. When you are using something when you are trying to evaluate your forces at the next time step, it's another strategy. It's called an implicit integration scheme. Sorry, I'm 25. Just to give you the advantages and drawback of each of them, explicit schemes will be known to be efficient, but they will require to use a very fine time step, a very small time step. So it means you will have possibly a slow simulation if you need to use very, very small time steps. If you advance from 10 to the power of minus 3 seconds, you will need a lot of steps, for instance, to compute 1 second. You will need 1,000 steps to compute 1 second. So depending on your phenomenon, it may be a bit, finally, slow to compute the whole phenomenon. At the inverse, implicit schemes, they have the opposite behavior. They allow you to use large time steps, but the resolution of the physics will be a bit more complex. In both cases, they will define what goes in the A matrix and what goes in the B vector. I could have shown you maybe one example using the LR explicit. Explicit tells you the LR explicit is that f depends only of x of t. What do we have in the A matrix? The mass matrix. What do we have in the B vector? The forces at the current, using the current state of our object. As again, this is acceleration, you know, here. So acceleration is equal to the delta of velocity divided by the delta of time. Right? So far, so good. Just know that insofar we solve things not in acceleration, but in delta of velocity. So that's the difference between the current velocity and the velocity at the next time step. And therefore, we put the time step on the other side of the equation. So this is how we solve. It's completely equivalent, and it's just the time step is sent to the other side of the equation. All right. So you see that once you've selected one integration scheme, you are able to define what goes in the A matrix and what goes in the B vector. But the integration scheme is not in charge of solving this. The one in charge is the so-called linear solver, and that was, I think, your point, Carolina, earlier. You know, what is one, what is CG, why using this one, and so on. This is the family of linear solvers and the theory which is behind. There is two families, the direct solvers trying to inverse the A matrix, and iterative processes like the conjugate gradient, that's the equation for the conjugate gradient, where what do? You make some kind of optimization in order to reduce this residual. Basically, you optimize iteratively your solution. That's the two kind of families for linear solvers. Anyway, both, what they aim at doing is to find the new solution of our system, Ax equal b. Insofar, what we're looking at is delta v. It's a delta of velocity. So once we found that, we can update the new velocity of each of the nodes, and we can subsequently update each of the position of the mesh. And this is done at each time step. when we open the run sofa, I'll get back to just it was the other one here. When we open run sofa here, and when I'm clicking on animate, there is no magic under the hood. What happens is that in the graphical user interface of Sofa, we connect the button animate to the function of the simulation called animate. It triggers what? The animation loop. If you look at the code, you will have direct calls from one to another. So you press the button, it calls the animation loop, and it calls, in that case, the step function of the animation loop. You remember we said the default animation loop? 2 steps. Collision detection, and we solve the mechanics, we solve the physics. And to solve the physics, we connect to the integration scheme. Okay, let's have a look to the code. In the step function of the default animation loop, we have a function called animate. This function contains 2 steps, 2 main steps, which are collision detection and solve the resolution of the physics. So exactly the ones we detailed so far. If we check in the code, we will find that it calls 2 things, the collision pipeline, and it will call each integration scheme, and it will call the function solve. All right? I'm just checking at the term. So that's the 2 steps that we mentioned so far. So that was what happened with the default animation loop, connecting to the implicit here, calling the solve function of the Euler implicit scheme to solve the physics of our rigid particle moving, pushed along the x direction due to the constant force. I will skip this. Actually, all the functions that are actually called in the process that we followed with the rigid particle. But if we want to summarize here, we understood the structure of a simulation, the fact that we had this root node opening the simulation, that we had to structure that with child nodes and so on. The role of the animation loop that was ruling the steps within one time step. We understood the relationships between components. We used also mesh loaders. You know, they're completely passive. They load a mesh. They load the whole topology. And usually we connect that to a topology container or a mesh topology. We added some physics, a mass, an external force, a mechanical constitutive law. Without any integration scheme and linear solvers, it was not moving. So we always need to remember to have something that defines us how to go from one time step to another and how to solve the AX equal B problem. And after that, once we move to a deformable object, when we move to this deformable lever, we started to add a rendering model, a collision model, and we use the mappings always to connect those to the mechanics. This can be done using XML, Python scripting, and again, Python scripting, we just uncovered slightly that you can access many things, you can change anything you like while the simulation is running, and that's something which is definitely more and more used in the community for interactivity purposes. So that's, I'm trying to avoid to go too much, especially at the end here, to go too much into the equation. So that's the reason why I, on purpose, skipped a few slides to avoid making things too easy at the end or a bit too dense. I think it was already a bit too dense or a bit too long. But That's, as we said at the beginning, a way to create a large overview of what SOFA can do, how SOFA is working, how it is actually, how the whole pipelines are working, the animation loop, the collision pipeline, the physics resolution, and how things are actually implemented in SOFA. And on each of those topics, again, we could dig in later on in some other sessions. That's really up to you. But that's the first, I would say, first uncovering, first experience with SOFA that I'd like to highlight and to show so that you can have a first smooth start with SOFA, avoiding to get too many surprises when running simulations. Thank you for the attention, because it was like, I know it's like 7 hours long. It's a bit dense and intense maybe to follow up to the end, just for attention reasons. And yeah, I hope it clarified a bit things, or at least it gave a good first insight about what is SOFA and what you could actually do with SOFA. If you have any question, I would be happy to take them. If you have like or suggestions for changes, I would be happy also to take them.
Is it possible to have these slides?
Yeah, definitely. As I mentioned that at the beginning of the session, I will definitely send you the slides. It will be under like a PDF format, but I think it's good. It's working also this way. But yeah, it will be PDF format of the slides. Yeah, you just won't have the animations, obviously, in the PDF version.
No question from my side, but thank you very much, Hugo, for this training.
You're welcome. And really, what matters to me the most would be that you take your own, I would say, your own experience with SOFA. You start really using SOFA or the simulation that has been provided by others to you for running your first SOFA simulations. I would suggest to gather a list of questions. The more you use, the more questions should actually arise around what you've done. And once you think you gathered enough of them, or you reach a point where there is too many questions for you to pursue, let's retake contact, and I would be happy to make another session. Like, either we take an hour and we just chit chat about the questions you have, or if you have on top of the questions you have already specific focus that you would like to address, we could do that as well. Okay.
Perfect.
Okay. Yeah. Thank you.
Thank you very much.
You're very welcome. Have a good day, guys. And yeah, if you have any questions in the coming days, do not hesitate to contact me directly per email, and I will send you all the materials, obviously, as I mentioned before.
Okay.
Thank you. Have a good day.
Bye.
Bye.
Bye-bye.